We've all looked up at the night sky and wondered about the mysteries of the universe. We hear things, read things, and sometimes what we think we know about space just isn't quite right. It turns out, a lot of what's commonly believed about the cosmos is actually based on myths and misunderstandings. Scientists are constantly learning more, revealing a universe far more complex and fascinating than we often imagine. In this video, we're diving headfirst into the universe to debunk 30 of the most popular space myths out there. We'll explore everything from black holes to the idea of sound in space, using real scientific facts to show you the true story. Get ready for an eye-opening journey that will challenge some of your deepest held beliefs about space and uncover the amazing reality. Stick around to the very end because you might be surprised to find out which of these myths you thought were true. Alright, let's kick things off with a myth you probably see every single day, quite literally. Look up at the sky on a clear afternoon, and what color is the sun? Most of us would immediately say yellow, perhaps even drawing it that way since childhood. But here's the fascinating truth: the sun isn't actually yellow. That golden or yellowish hue we see is an illusion created by our Earth's atmosphere. Think of the atmosphere as a giant prism. It scatters sunlight, specifically the blue and violet light, more effectively than other colors. This is why the sky appears blue, and as the blue light is scattered away, the remaining light heading towards our eyes on the ground looks warmer, shifting towards yellow, orange, and even red during sunrises and sunsets when the light travels through more atmosphere. Now, if you could somehow view the sun from space outside of our atmosphere, you'd see it for what it truly is: a brilliant white. That's because sunlight contains all the colors of the visible spectrum mixed together in roughly equal proportions. When your brain receives light with all these colors combined, you perceive it as white. Scientists categorize stars like our sun based on their temperature and the type of light they emit, a concept known as blackbody radiation. The sun's surface temperature, around 5,500 degrees Celsius, means its light peaks in the yellow-green part of the spectrum. But because the emission curve is broad and includes light across the entire visible range, and even into infrared and ultraviolet, the combined effect is white light, not just yellow. Our atmosphere just filters out some of that light before it reaches us, changing its apparent color. So, while those sunny yellow drawings are cheerful, the scientific reality of a white hot star is even more incredible. Now, let's tackle another persistent myth, one that's perhaps even more widely believed than the sun being yellow. You've probably heard it said that the Great Wall of China is the only man-made structure visible from space with the naked eye. It sounds impressive, right? A testament to human engineering on such a grand scale that it can be seen from orbit. But the reality is, this is simply not true. Even from relatively low Earth orbit, the Great Wall is extremely difficult, if not impossible, to spot without aid. Think about it this way: the Great Wall, while incredibly long, is also relatively narrow, only about 6 meters wide in most places. While its length is impressive, its width just isn't substantial enough to stand out against the varied terrain of the Earth from hundreds of kilometers up. Compare that to something clearly visible from space, like major highways, which are multiple lanes wide and often flanked by cleared land, or even better, the dazzling sprawl of city lights at night. Those urban areas are massive, sprawling patches of illumination that are unmistakable from orbit. Astronauts who have spent time on the International Space Station, which orbits at about 400 kilometers above Earth, consistently report how hard it is to see the Great Wall. Many say they can't see it at all without using binoculars or powerful telephoto lenses, and even then, it requires knowing exactly where to look and having ideal lighting and atmospheric conditions. It's not like seeing the vast patterns of deforestation, the bright blue of large lakes, or the distinct lines of major river systems, all of which are readily apparent. Our ability to see things from space is limited by the resolution of our eyes and the distance involved. From orbit, the Great Wall essentially blends into the natural landscape. It doesn't have a distinct color or reflective quality that makes it stand out. So, while the Great Wall is an incredible historical and architectural achievement, its visibility from space is unfortunately just a myth that continues to endure. Now, let's move on to a myth that's perhaps one of the most stubborn and widely debated: the idea that the moon landing was faked, despite overwhelming evidence to the contrary. The conspiracy theory that NASA staged the Apollo missions, particularly Apollo 11 in 1969, persists for many. Proponents of the hoax theory often point to several key pieces of evidence that they claim prove the landings were filmed in a studio on Earth. One of the most common arguments revolves around the American flag planted by the astronauts. They question why the flag appears to be waving in photographs when there's no wind on the moon. The explanation is simple and scientific: the flag wasn't actually waving. It was designed with a rod sewn into the top edge to hold it out and make it look like it was flying, as there's no atmosphere or wind on the moon to do so naturally. The creases you see in photos are just folds from being packed tightly during the journey. Another frequent claim is that there are no stars visible in the lunar landing photographs. This might seem strange given that space is full of stars, but again, there's a straightforward scientific reason. The photographs were taken during the lunar daytime, with the sun brightly illuminating the lunar surface and the astronauts in their brilliant white spacesuits. To properly expose the images for the bright foreground, the camera settings had to be adjusted, resulting in a short exposure time. This setting was perfect for capturing the details on the moon, but simply didn't allow enough light from the much fainter, distant stars to register on the film. It's similar to how you can't see stars in photos taken during the day on Earth. The sun and the brightly lit moon surface were the dominant light sources by far. Then there are the shadows. Some hoax theorists argue that the shadows in the photos appear to run in different directions, suggesting multiple light sources like studio lights, not just the sun. However, this is a misinterpretation caused by the uneven lunar terrain and perspective. The sun is an incredibly distant point source of light, meaning its rays are effectively parallel when they reach the moon. Just like on Earth, shadows cast by parallel light sources can appear to converge or diverge depending on the angle of the ground and your viewpoint in the photograph. The lunar landscape isn't a flat, even plane, so shadows behave exactly as you'd expect from a single, distant light source like the sun when viewed from different perspectives over undulating ground. Beyond debunking these specific points, there is a mountain of verifiable evidence that proves the moon landings were real. For decades, scientists have used lunar laser ranging experiments, bouncing lasers off reflectors left on the moon by the Apollo astronauts. Tracking the time it takes for the laser light to return allows us to precisely measure the distance to the moon, and these reflectors are undeniably on the lunar surface. We also have hundreds of kilograms of moon rocks brought back by the Apollo missions, which have been studied by scientists worldwide and have properties distinct from any rocks found on Earth. Furthermore, images and data from subsequent lunar missions by other countries, like Japan's Selene mission and India's Chandrayaan mission, have captured photos and data of the Apollo landing sites, clearly showing the remnants of the lunar modules, tracks left by the astronauts, and scientific equipment. The evidence is concrete and comes from multiple independent sources, confirming that humans did indeed walk on the moon. You know, when we see movies about space travel, particularly sci-fi adventures, there's a scene that pops up again and again. A spacecraft dodging and weaving through a dangerously dense field of asteroids, narrowly avoiding collisions. It's a thrilling visual, creating high-stakes drama as the heroes navigate this treacherous cosmic obstacle course. But here's the reality check. That cinematic depiction of asteroid belts is another pervasive space myth. In truth, asteroid belts, even the main belt located between Mars and Jupiter, are nothing like those crowded free-for-alls you see on screen. The sheer size of space means that even in supposedly dense areas like asteroid belts, individual objects are incredibly far apart. To give you a sense of the scale, the main asteroid belt contains millions of asteroids, but they are spread out over a colossal volume of space. If you were to stand on one asteroid in the main belt, the next one large enough to be considered significant would likely be hundreds of thousands, even millions of kilometers away. Imagine trying to navigate your way through a region the size of an ocean, but instead of ships, you have pebbles scattered miles apart. That's a much closer picture of what traversing an asteroid belt is actually like. This is why spacecraft like the Voyager probes, which have journeyed to the outer solar system and beyond, and the New Horizons probe on its way to Pluto and the Kuiper belt, have passed through the main asteroid belt without incident. They didn't need to perform daring dodges or intricate maneuvers to avoid crashing into asteroids. Their trajectories were simply planned, and they sailed through with vast amounts of empty space around them. The dangers to spacecraft in these regions aren't from constant near misses with large asteroids, but rather from tiny dust particles, which can still cause damage at high speeds, and the challenges of communication over immense distances. So, next time you see a movie depicting a chaotic asteroid field, remember the scientific reality. Space is mostly empty, and even in asteroid belts, there's a whole lot of nothing between those rocks. Here's another common misconception that a lot of people have, that there's no gravity in space. You see astronauts floating effortlessly in videos, and it's easy to think they've escaped Earth's pull completely. But if there were no gravity in space, the Moon wouldn't orbit the Earth, and the Earth wouldn't orbit the Sun. Gravity is a force that exists everywhere in the universe, exerted by any object with mass. The more massive an object, the stronger its gravitational pull. While gravity does get weaker with distance, it never truly disappears. You might wonder then, why are astronauts on the International Space Station, or ISS, floating? It's not because there's no gravity there. In fact, at the altitude of the ISS, about 400 kilometers above Earth, gravity is still about 90% as strong as it is on the ground. The reason they experience weightlessness is because they are in a continuous state of freefall. Imagine throwing a ball horizontally. It falls towards the ground as it moves forward. Now imagine throwing it incredibly fast. It would still fall, but over a much greater distance before hitting the ground. Now imagine throwing it so fast that as it falls towards the curved surface of the Earth, the surface curves away at the same rate. That's essentially what's happening with the ISS and everything inside it. The station is moving sideways at an incredible speed, roughly 28,000 kilometers per hour. As it moves horizontally, Earth's gravity is constantly pulling it downwards, but because of that high speed, the station falls around the Earth rather than into it, creating an orbit. Everything inside the station is also falling at the same rate and in the same direction as the station itself. Since they are all falling together, side by side, it feels like they are weightless relative to each other. It's the same sensation you temporarily feel at the top of a roller coaster just before it plunges down. You're in free fall, and for a moment you feel weightless. So the term zero gravity in space is misleading. Microgravity, or weightlessness due to freefall, are much more accurate descriptions of what's happening on the ISS and other orbiting spacecraft. Another persistent myth, often fueled by science fiction, is that black holes are like cosmic vacuum cleaners, actively sucking up everything in their path. The image is often of a voracious monster in space, indiscriminately devouring stars and planets. While it's true that black holes have incredibly strong gravitational pull, the reality is much less aggressive and far more nuanced. A black hole's gravity is indeed immense because a tremendous amount of mass is packed into an incredibly small space. However, this powerful gravity only dominates over relatively small distances. Think of it this way: gravity follows the inverse square law, meaning its strength decreases rapidly as you move further away from the source. For an object to be pulled into a black hole, it needs to get extraordinarily close, much closer than you might imagine. There's a critical boundary around every black hole called the event horizon. This is the point of no return. Once something crosses the event horizon, nothing, not even light, can escape its gravitational grip. The size of this event horizon is determined by the black hole's mass and is known as the Schwarzschild radius. However, outside of the event horizon, a black hole's gravity behaves just like the gravity of any other object with the same mass. Let's consider a mind-bending thought experiment. What would happen if our sun were suddenly replaced by a black hole with the exact same mass? Would the Earth be instantly sucked in? Surprisingly, no. Our planet's orbit around the Sun is determined by the Sun's mass and the distance between the Earth and the Sun. If you swap the Sun for a black hole of equal mass, the gravitational force at Earth's distance wouldn't change at all. The Earth would continue to orbit the black hole exactly as it orbits the Sun now. The danger only arises if Earth were to stray incredibly close to the black hole, crossing its event horizon. In reality, black holes often exist within swirling disks of gas and dust known as accretion disks. Material in these disks doesn't get instantly sucked in. Instead, it orbits the black hole at tremendous speeds, slowly spiraling inwards due to friction and turbulence within the disk. This process can take a very long time, and much of the material in an accretion disk never actually falls into the black hole. It might be channeled into powerful jets or simply remain in orbit. So, while their gravity is extreme, black holes aren't indiscriminate cosmic vacuum cleaners. They are powerful gravitational wells, but you have to get remarkably close to fall in. Thinking about the vastness of space, it's easy to picture it as completely empty, a perfect vacuum where nothing at all exists. This idea that space is an absolute void is another common myth. While space is indeed incredibly empty compared to anything we experience on Earth, it's not actually a perfect vacuum. There are always trace amounts of stuff floating around, even in the seemingly vast emptiness between stars and galaxies. We call the material that exists between stars within a galaxy the interstellar medium. It's made up of gas, mostly hydrogen and helium, along with tiny dust grains composed of heavier elements like carbon and silicon. This gas and dust, while extremely diffuse, meaning spread very thinly, is the raw material for new stars and planets. It's not like the air you breathe, where molecules are constantly bumping into each other. The particles in the interstellar medium are incredibly far apart on average. Even more sparsely distributed is the intergalactic medium, which is the stuff found between galaxies. This is even thinner than the interstellar medium, but again, it's not completely empty. It also contains gas and some particles left over from the early universe or expelled from galaxies. Beyond just gas and dust, space is also permeated by high-energy particles and radiation. Cosmic rays, for instance, are energetic particles, often atomic nuclei, traveling at nearly the speed of light. They originate from sources like supernova and black holes and stream through space, constantly bombarding our atmosphere. We also have neutrinos, tiny, nearly massless particles that interact very weakly with other matter. Trillions of neutrinos pass through your body every second, originating from the sun, supernova, and other cosmic events, moving through space unimpeded. Theoretically, even in what seems like empty space, there are quantum fluctuations, a concept related to zero-point energy. This is a more complex idea from quantum mechanics, suggesting that even in empty space, there are minimal energy levels and fleeting particle-antiparticle pairs constantly popping into and out of existence. So, while space is remarkably empty by terrestrial standards, it's a far cry from an absolute void. It's a dynamic environment, home to diffuse matter, energetic particles, and perhaps even the subtle hum of quantum activity. Have you ever thought about what truly powers the sun? Many people picture it as this enormous ball of fire, maybe like a campfire on an unimaginable scale, burning away in space. It feels intuitive, right? Fire gives off light and heat, and the sun does too. But that idea, while common, is actually another big space myth. The sun isn't burning in the way a log burns in a fireplace or a candle flickers. What we see as the sun's light and warmth doesn't come from a chemical reaction like combustion, which is what fire is. Fire is a process where a substance reacts rapidly with oxygen, releasing heat and light. The sun's energy source is fundamentally different and far more powerful. It's nuclear fusion. Deep within the sun's core, under conditions of unimaginable pressure and temperatures reaching millions of degrees Celsius, hydrogen atoms are forced together. These incredible forces overcome the natural repulsion between the positively charged protons in the hydrogen nuclei. When 4 hydrogen nuclei are squeezed together, they fuse to form a single helium nucleus. And here's the amazing part: the resulting helium nucleus is slightly less massive than the 4 original hydrogen nuclei combined. That tiny bit of missing mass isn't just gone. It's converted into a tremendous amount of energy according to Einstein's famous equation, E equals mc squared. This energy then slowly makes its way to the sun's surface and radiates out into space as light and heat, sustaining life on Earth. Chemical burning or combustion releases energy by rearranging atoms, breaking and forming chemical bonds. Nuclear fusion, on the other hand, involves changing the very nuclei of atoms, and the energy released from this process is millions of times greater per unit of mass compared to even the most energetic chemical reactions. Think of it like this: a tiny amount of material undergoing fusion releases an amount of energy equivalent to burning millions of tons of coal. The scale of energy generation from nuclear fusion is what allows the sun to shine so brightly for billions of years. For nuclear fusion to occur, you need those extreme conditions, temperatures high enough for atomic nuclei to move with incredible speed, overcoming their electrical repulsion, and pressures so immense they force these nuclei close enough together to fuse. These conditions are only met in the very dense, hot core of stars like our sun. So, while the visible effect might look a bit like fire from a distance, the process powering the sun is a spectacular example of nuclear physics on a cosmic scale. It's not burning, it's fusing. Following the idea of what makes a planet livable, there's a myth that often comes up, that Earth is the only place in the universe with liquid water. For a long time, it was easy to believe. Our planet is covered in oceans, rivers, and lakes, clearly a world bathed in liquid water. But our understanding of the solar system and beyond has expanded dramatically, and the scientific consensus is now very different. It turns out liquid water isn't as rare in the cosmos as we once thought. While Earth is unique in having vast amounts of liquid water on its surface, evidence is mounting that substantial bodies of liquid water exist elsewhere, particularly beneath the icy crusts of moons in the outer solar system. Take Jupiter's moon Europa, for example. Data from spacecraft like Galileo strongly suggest that beneath Europa's cracked, icy shell lies a vast ocean of salty liquid water, possibly deeper than Earth's oceans. The energy generated by Jupiter's immense gravity through tidal forces, flexing and warming Europa's interior, is believed to be enough to keep this subsurface ocean liquid. Similarly, Saturn's moon Enceladus has provided even more compelling evidence. The Cassini spacecraft observed geysers erupting from cracks near Enceladus's south pole, spewing plumes of water vapor and ice particles into space. Analyzing these plumes revealed they contain salts and organic molecules, strong indicators that they originate from a liquid water ocean beneath the ice, interacting with a rocky seafloor. These subsurface oceans are incredibly exciting because they offer environments where liquid water, a key ingredient for life as we know it, could persist, shielded from the harsh radiation of space. And it's not just moons. Mars likely had vast amounts of liquid water on its surface billions of years ago, evident in dry riverbeds, ancient lake beds, and mineral deposits that form only in the presence of water. While liquid water is unstable on the surface of Mars today due to its thin atmosphere and low temperature, the search continues for evidence of subsurface liquid water or pockets of ice that could melt. Beyond our solar system, the discovery of thousands of exoplanets, planets orbiting other stars, has opened up incredible possibilities. Scientists are actively searching for exoplanets in the habitable zone around their stars, the region where temperatures are just right for liquid water to potentially exist on a planet's surface. While confirming liquid water on a distant exoplanet is challenging with current technology, the sheer number of planets being discovered suggests that worlds with liquid water are likely out there. The potential discovery of liquid water on other celestial bodies is a pivotal moment in the search for life beyond Earth, making the idea that our planet is the only place with this precious substance a myth firmly rooted in a less informed past. For centuries, astronomers marveled at what they saw through their telescopes, noticing what appeared to be straight lines or channels on the surface of Mars. These features fueled speculation for a long time, leading to the popular myth that these were canals built by intelligent Martians. This idea gained significant traction in the late 19th and early 20th centuries, largely thanks to observations by astronomers like Percival Lowell, who enthusiastically mapped intricate networks of these canals and believed they were irrigation systems built by a dying civilization struggling to transport water across their arid planet. It's a captivating thought, a notion of alien life just next door, and it captured the public imagination, influencing early science fiction stories. However, as telescopes improved and crucially as spacecraft began visiting Mars, our understanding of the Martian surface changed dramatically. The Mariner and Viking missions of the late 20th century provided much clearer images than ground-based telescopes could. These close-up views revealed that the straight lines and networks Lowell and others thought they saw were simply optical illusions. Under better resolution, the canals resolved into natural geological features like craters, mountains, valleys, and irregular terrain. Our brains are remarkably good at finding patterns, sometimes even when none truly exist, and the limitations of early telescopes likely contributed to observers connecting disparate dark spots or subtle variations in shading into perceived straight lines. Furthermore, the Martian atmosphere is very thin, and surface pressure and temperature conditions are such that liquid water is generally unstable on the surface today. While there is strong evidence for liquid water existing on Mars in the distant past, the idea of a civilization building massive canal systems to manage it is scientifically unsupported by everything we know about the planet's current and past conditions. The myth of Martian canals is a fascinating example of how limited data and human interpretation can lead to compelling but ultimately incorrect conclusions about other worlds. It reminds us that while imagination is crucial in exploration, scientific progress requires rigorous observation and verification to separate fascinating speculation from reality. Today, we know Mars is a world of incredible and varied geology, but those straight-line canals built by aliens, that's one myth that has been thoroughly debunked by robotic explorers. Turning our attention skyward again, a dramatic and often depicted scenario in movies involves stars exploding with a blinding flash and a tremendous boom that echoes through space. It's an intense image, a cataclysmic event accompanied by powerful sound waves. But here's a fundamental fact about space that makes this scenario, at least the audible part, impossible. In space, there is no sound. This might seem counterintuitive when you picture massive cosmic events like supernova explosions, which indeed release staggering amounts of energy. However, sound as we experience it is a wave that travels through a medium like air, water, or solid material. Sound waves are essentially vibrations, compressions, and rarefactions of the particles within that medium. When something makes a sound, it causes the surrounding medium to vibrate, and those vibrations propagate outwards. On Earth, we hear sounds because these vibrations travel through the air, reach our eardrums, and are interpreted by our brains. Space, conversely, is very nearly a vacuum. While we just talked about how space isn't perfectly empty, the particles that do exist are so incredibly far apart that they cannot effectively transmit sound waves. There isn't enough matter to carry the vibrations from one point to another. Imagine trying to send a ripple across a vast, almost empty swimming pool with only a few drops of water scattered across the surface. It's just not going to happen. So, when a star explodes in a supernova, it is an unbelievably violent event, releasing vast amounts of energy in the form of light, radiation, and particles. These forms of energy do travel through space. We can see the light from supernova, detect the radiation, and even measure the stream of particles they emit. But the explosive force, the shockwave itself, has no medium to push against to create audible sound waves that could travel across the vacuum. While scientists can translate other forms of energy from space, like radio waves or plasma waves, into audible sounds for data analysis or demonstration, these are representations, not the actual sound of the cosmic event in space itself. The silence of space, despite the incredible power of the events happening within it, is a fundamental consequence of its emptiness. Let's explore another common misconception about our solar system, one that many of us might carry from early science classes, that the planets are neatly lined up in order from the Sun, spinning in predictable side-by-side orbits. While it's true that planets orbit the Sun in a specific sequence based on their distance, they are definitely not lined up in a straight row at any given time, and their orbits are far from being perfectly aligned flat disks like rings on a target. In reality, the orbits of the planets in our solar system are tilted relative to each other. Imagine a flat plane extending outwards from the Sun, called the ecliptic plane, which is roughly the plane of Earth's orbit. Most of the other planets orbit relatively close to this plane, but their orbital paths are inclined at different angles. For example, Mercury's orbit is tilted by about 7 degrees relative to the ecliptic, while Venus is slightly over 3 degrees, Mars just under 2 degrees, and so on. Even the orbits of the outer planets like Neptune and Uranus have slight inclinations. These tilts mean that as the planets travel in their orbits, they are constantly at different positions above or below this central plane. It's like a set of rings that are all slightly askew rather than perfectly stacked. Furthermore, the planets are all moving at different speeds in their orbits, with the inner planets moving much faster because they have less distance to cover and are more strongly pulled by the Sun's gravity. Because of these varying orbital periods and inclinations, the planets are very rarely, if ever, precisely lined up in a straight line from the Sun. Even when planets appear to be close together in the night sky from our perspective on Earth, which we call a conjunction, they are usually still vastly separated in three-dimensional space, just aligned along our line of sight. The closest the planets might come to a line up is when they are all on the same side of the Sun, within a relatively narrow arc of the sky, which happens only very infrequently over long timescales. However, even during such events, they are still spread out over wide angles relative to the Sun and at different distances, certainly not forming a perfect straight line. The idea of planets lining up like beads on a string is a simplified model that doesn't reflect the dynamic, three-dimensional nature of their orbits. There's a visually striking image often associated with astronauts or spacecraft in space, catching fire or exploding in flames. Whether it's a character's spacesuit igniting after a breach or a starship erupting in cinematic glory, fire in the vacuum of space seems like a logical consequence of damage or malfunction, especially with all that fuel and complex equipment around. However, the reality is that fire, as we understand it, requires oxygen, and space is, as we've discussed, largely a vacuum. Fire is a rapid chemical process called combustion, which involves a fuel source reacting with an oxidizer, most commonly oxygen, in the presence of heat. On Earth, our abundant atmosphere provides the oxygen needed for things to burn. In the vacuum of space, there is essentially no free oxygen to sustain a flame. So, if a spark occurs or something overheats in space outside of a pressurized and oxygenated environment like a spacecraft cabin, you won't get a fire that resembles what you see on Earth. Material might melt, vaporize, or decompose due to heat, but without an oxidizer, it cannot undergo combustion and produce flames in the typical sense. Within a spacecraft or space station, which are pressurized habitats with breathable air containing oxygen, fire is a very real and dangerous threat. Because the air inside is a controlled environment, a fire can indeed start and spread rapidly, which is why space habitats have extensive fire detection and suppression systems. However, the image of a spacecraft spontaneously bursting into flames in the vacuum is misleading. If a fuel source were to leak into space, it might rapidly disperse or freeze, but it wouldn't ignite into a fireball without an external source of oxygen. Explosions in space, while certainly possible, are not necessarily fiery. They could be caused by rapid expansion of gases, structural failure under pressure, or the release of stored energy, but the production of flames still requires an oxidizer. The dramatic visual of fire consuming objects in the vacuum of space is largely a creation of fiction, ignoring the fundamental requirement of oxygen for combustion. Moving on, let's address a myth related to size and proportion in the solar system. You often see diagrams or models of the solar system where the planets are shown as relatively large circles around a somewhat larger sun, with distances between them looking quite manageable. This leads some people to believe that the planets are much larger relative to the distances between them than they actually are, or perhaps that the Sun is only slightly larger than the planets. The truth is, the vastness of space is incredibly difficult to represent to scale, and most illustrations we see significantly distort the sizes and distances to make them understandable. The reality is that the Sun is absolutely enormous compared to any of the planets. You could fit over 1 million Earths inside the Sun. Jupiter, the largest planet, is still only about 1/10 the Sun's diameter. The Sun contains over 99.8% of the total mass of the entire solar system. The planets are, by comparison, tiny specks orbiting a colossal star. And the distances between these objects are staggering. If you were to build a scale model of the solar system where the Earth was the size of a marble, the Sun would be about the size of a car and placed about 200 meters away. Neptune, the farthest planet, would be thousands of kilometers away in this model, potentially in a different state or even country. Even the distance between Earth and the Moon, which seems relatively close, is about 30 times the diameter of the Earth itself. Trying to visualize this true scale makes it clear why depicting the solar system accurately in a single diagram is nearly impossible. If you showed the planets to scale, the distances would require a diagram miles wide, and if you showed the distances to scale, the planets would be microscopic, invisible dots. So, when you see a diagram of the solar system with nicely sized planets relatively close together, remember that it's a necessary simplification, and that the true scale involves a much larger, more dominant sun and incredibly vast stretches of empty space between the tiny planetary bodies. Here's a myth that Hollywood loves to perpetuate, that you can easily talk or hear explosions in space without any special equipment. Characters in movies often communicate verbally while floating outside their spacecraft, or dramatic cosmic battles are accompanied by loud booms and crashes. This directly contradicts the truth we discussed earlier about sound needing a medium to travel. Since space is essentially a vacuum, there's no air or other substance for sound waves to propagate through. Therefore, if you were outside a spacecraft in space without a radio, you couldn't speak to someone next to you, and you wouldn't hear a sound if a meteorite struck a nearby object or a star exploded in the distance. Communication in space relies entirely on electromagnetic waves, primarily radio waves. These waves don't need a medium to travel. They can propagate through the vacuum of space at the speed of light. That's how mission control on Earth communicates with astronauts on the International Space Station, or how signals are sent to and from distant probes like the Voyagers. Astronauts working outside their spacecraft use radios within their suits to talk to each other and back to the spacecraft or Earth. Their helmets and suits are pressurized and contain air, allowing sound to travel from their vocal cords to a microphone, which then converts the sound into a radio signal. That signal is transmitted and received by another radio, which converts it back into sound that the listener can hear through headphones. Without this technology, there would be complete silence. The sounds you hear in documentaries or movies depicting space are typically added for dramatic effect, or are artificial soundscapes created from data like pressure waves or plasma oscillations that have been converted into audible frequencies. While these can be scientifically interesting ways to represent data, they are not the actual sounds you would hear in the vacuum of space. So, the next time you watch a space movie with dramatic sound effects during an external scene, remember that the reality of space is a lot quieter than the soundtrack suggests. It's a classic sci-fi trope depicted in countless films and books. Astronauts exposed to the vacuum of space instantly freezing solid due to the extreme cold. The image of a body flash frozen solid is certainly dramatic and horrifying. However, this is another significant myth about the effects of the space environment. While the temperature in space can be incredibly cold, especially in the shade away from any direct sunlight, you wouldn't instantly freeze. The primary ways heat is lost from a body are through conduction, convection, and radiation. Conduction is heat transfer through direct contact, and convection is heat transfer through the movement of a fluid like air or water. In the vacuum of space, there's no significant medium for conduction or convection to occur. The only way a body in space would lose heat is through radiation, which is the emission of electromagnetic waves. This process is much slower than conduction or convection, especially from a human body. Think about a thermos bottle designed to keep liquids hot or cold. It works by creating a vacuum layer between the inner and outer walls to minimize heat transfer by conduction and convection. Similarly, a body exposed to the vacuum of space would lose heat through radiation, but it would take a considerable amount of time to freeze solid. Moreover, other dramatic effects would occur much sooner and be far more immediately dangerous. The sudden lack of external pressure would cause any liquids in the body to vaporize rapidly. Water in tissues and blood would turn to gas, causing the body to swell significantly, though the skin is elastic enough that you wouldn't explode. The gases already in your lungs would also expand rapidly. You would also experience the effects of decompression and lack of oxygen, losing consciousness within seconds due to hypoxia. While eventually, over a longer period, the body would succumb to the cold and eventually freeze, it wouldn't be an instant deep freeze like in the movies. So, while exposure to the vacuum of space is absolutely fatal and terrifying due to decompression and lack of air, the myth of instantaneous freezing is scientifically inaccurate. Another common misconception relates to the appearance of planets, specifically their color. When we see images of planets like Mars, it's often depicted as vividly red, earning it the nickname the Red Planet. Jupiter is shown with distinct bands of orange, white, and brown, and Neptune appears a striking blue. We see these colors in photographs taken by spacecraft and telescopes and assume that's exactly how they would look to the human eye if we were floating nearby. However, many of the stunning color images we see of planets are actually false color or enhanced color images. Scientists use these techniques to highlight specific features, atmospheric compositions, or mineral distributions that wouldn't be as apparent in natural color. Different filters on cameras capture light in specific wavelengths, including wavelengths outside the visible spectrum that our eyes can't see, like infrared or ultraviolet. These images are then processed on computers, and different colors are assigned to different wavelengths or combinations of wavelengths to make certain details stand out. For example, an image of Mars might be color-enhanced to emphasize the difference between areas rich in iron oxide's rust, which is red, and areas with different mineral compositions, making the red more pronounced than it would look to the naked eye. Similarly, images of gas giants like Jupiter and Neptune often use enhanced color to bring out subtle variations in their cloud layers or atmospheric chemistry that would otherwise appear muted or less distinct. While Mars is indeed red due to iron oxides, and Neptune is genuinely blue because methane in its atmosphere absorbs red light and reflects blue, the intensity and specific hues in many publicly released images are often the result of scientific processing to reveal more information than a simple photograph would. This doesn't mean the images are fake. They are accurate representations of data, but they are not always a one-to-one depiction of what your eye would perceive. So, while planets certainly have true colors based on their composition and atmosphere, the vibrant, sometimes almost surreal colors you see in many popular images are often scientifically enhanced to provide us with a deeper understanding of these distant worlds. When contemplating the vast scale of the universe and the sheer number of stars and galaxies, it feels almost inevitable that there must be intelligent life out there somewhere. The idea that we are the only intelligent beings in this boundless cosmos seems statistically improbable to many. This line of thinking has led to a kind of informal myth that because the universe is so big, the existence of intelligent alien life is a certainty. While the vastness of the universe certainly makes the possibility of life elsewhere plausible, even probable, the certainty of intelligent life is far from guaranteed and remains one of the most profound unanswered questions in science. The universe is indeed immense, containing billions of galaxies, each with billions or trillions of stars. Many of these stars likely host planetary systems, and among those planets, there may be billions or trillions located in the habitable zones where conditions could be suitable for liquid water and potentially life. This astronomical number of potential abodes for life is the basis for the argument that life must exist elsewhere. However, the jump from simple life like microbes to complex, intelligent, and technologically advanced life is where the significant uncertainties lie. We don't fully understand how life originated on Earth, let alone how common that process might be elsewhere. And even if life does arise, the evolutionary path towards intelligence and the development of a civilization capable of communicating across interstellar distances is incredibly complex and may involve a series of highly improbable steps. Consider the history of life on Earth. 4 billion years of evolution passed before technologically advanced civilization emerged. What if similar evolutionary paths are incredibly rare? The Fermi paradox highlights this very puzzle. If intelligent life is common, why haven't we seen any evidence of it? There are many possible explanations, from the vast distances and the difficulty of interstellar communication to the possibility that technological civilizations might be short-lived. While the search for extraterrestrial intelligence SETI continues, using radio telescopes and other methods to listen for signals, and while astronomers search for biosignatures in the atmospheres of exoplanets, we currently have no definitive proof of life beyond Earth, intelligent or otherwise. The universe's size certainly opens the door to the possibility, but until we find concrete evidence, the existence of intelligent alien life remains a compelling hypothesis, not a scientific certainty, and definitely not a debunked myth in the sense of a proven falsehood. It's a mystery we are still actively trying to solve, let's take a closer look at something a bit more down to Earth, or rather, something orbiting just above it, satellites. We use satellites for everything from GPS to communication and weather forecasting, and there's a common misconception about how many are up there and what space around Earth looks like because of them. You sometimes hear or see portrayals of near-Earth orbit as being absolutely choked with satellites, a dense swarm of objects that must make travel in space incredibly hazardous and complex. While it's true that there are thousands of active and inactive satellites, as well as debris orbiting Earth, the myth is that they create a literal, impenetrable shield or a jam-packed neighborhood. The reality is that the volume of space around Earth is enormous. Satellites orbit at various altitudes and inclinations, operating in different orbital paths. Low Earth orbit LEO, where the International Space Station and many communication satellites reside, extends up to about 2,000 kilometers above the surface. Geosynchronous orbit GEO, used by many weather and communication satellites, is much higher, around 35,786 kilometers. While there are thousands of objects in these regions, active satellites, defunct satellites, spent rocket stages, and fragments from collisions or breakups, collectively known as space debris, they are still incredibly spread out within these vast orbital shells. The probability of a random collision between any two specific objects is relatively low, though it does increase as the number of objects grows. The concern about space debris is real, and it's a significant challenge for the future of space exploration and satellite operations. Accumulating debris increases the risk of collisions, which can create even more debris, potentially leading to a cascade effect known as the Kessler syndrome, where collisions become so frequent that certain orbits become unusable. Space agencies and organizations track tens of thousands of objects in orbit to predict potential close approaches and maneuver satellites to avoid collisions. However, despite the thousands of objects, the space around Earth isn't a bumper car arena. It's a vast volume, and while the problem of debris is serious and requires management, the immediate environment is not a solid wall of satellites and junk as the myth suggests. The challenge isn't navigating through a dense crowd, but rather the risk posed by the sheer speed at which these objects travel. Even a small piece of debris can cause significant damage due to the high orbital velocities. Here's a myth that plays on fear and the unknown, that meteor showers, those beautiful streaks of light in the night sky, are dangerous events to be avoided, perhaps even posing a threat to life on Earth. We call them showers, and that sounds like things are raining down, which can evoke a sense of being bombarded. However, thinking of a meteor shower as a dangerous downpour of rocks is a misunderstanding of what's actually happening. Meteor showers occur when the Earth passes through a stream of cosmic debris left behind by a comet or sometimes an asteroid. As these small particles and dust grains enter Earth's atmosphere at extremely high speeds, they frictionally heat up and burn, creating the visible streak of light we call a meteor or shooting star. The particles are typically tiny, often no larger than grains of sand or small pebbles. They burn up completely long before they reach the Earth's surface. What you are seeing during a meteor shower is the fiery death of these tiny pieces of cosmic dust in the upper atmosphere, usually at altitudes of 70 to 100 kilometers. Larger pieces of debris from space, called meteoroids, can survive the fiery plunge through the atmosphere and land on Earth. At that point, they are called meteorites. But the objects that make up meteor showers are generally too small to survive this process. The vast majority of meteorites that do land on Earth are not associated with meteor showers and are random events. Historical records and scientific studies show no credible instances of a meteor shower causing harm to people or significant damage on the ground. In fact, meteor showers are safe and beautiful celestial events, a chance to witness cosmic dust turning into fleeting streaks of light as it disintegrates high above us. So far from being dangerous, meteor showers are something to look forward to and enjoy safely from the ground. Another commonly held belief about Mars is that it's a completely dead, unchanging planet, geologically inactive and devoid of dynamic processes. Because of its seemingly barren, rocky surface and lack of obvious volcanic activity like Earth has, it's easy to assume it's a static world, a frozen relic of the past. However, while Mars is not as geologically active as Earth, the idea that it's completely dead is a myth. Scientific missions to Mars, particularly orbiters and rovers, have provided evidence of ongoing geological activity and changes happening on the planet's surface today. We've observed phenomena like dust devils, which are swirling columns of wind that lift dust and carve patterns on the surface, constantly reshaping the fine regolith. We also see evidence of dust storms, which can grow to enormous sizes and even engulf the entire planet, dramatically changing its appearance from space. Beyond atmospheric activity, there's also evidence of more subtle geological processes. Repeated observations of certain slopes have shown changes that suggest what are called recurring slope lineae RSL, dark streaks that appear and grow downhill in warmer seasons and fade in cooler ones. One hypothesis, though still debated, is that these might be caused by briny, salty water flowing temporarily close to the surface, indicating some form of current hydrological activity, even if it's not pure liquid water. There has also been evidence suggesting recent volcanic activity in terms of relatively young lava flows found on the surface, though recent in geological terms can still mean millions of years ago. It indicates the planet is not entirely cold and inert in its interior. Furthermore, the constant bombardment by small meteoroids creates new impact craters on the surface over time. While Mars lacks plate tectonics and global volcanic chains like Earth, it is still a dynamic planet with its own ongoing geological and atmospheric processes. It's not a dead, frozen world, but rather a planet with different, less intense forms of activity than those we are most familiar with on Earth. When you look up at the night sky and see those quick, bright streaks of light flash across the darkness, what do you call them? Most people say shooting stars, and it's a beautiful, poetic image, but here's another space myth. Those streaks of light are not stars at all. The stars we see in the night sky are colossal balls of hot gas like our Sun, located incredibly far away in our galaxy and beyond. They are immense celestial bodies, and they certainly don't zip across our sky and disappear in a flash. What we call a shooting star is actually something much, much smaller and happening much closer to home. It's a small piece of rock or dust, often no bigger than a grain of sand or a pebble, that enters the Earth's atmosphere at incredibly high speed. As it plunges through our atmosphere, typically at tens of thousands of kilometers per hour, it experiences intense friction with the air molecules. This friction causes the little particle to heat up dramatically, sometimes glowing white-hot, and it rapidly burns up. The bright streak of light we see is not the particle itself as much as it is the superheated air around it and the glow of the vaporizing material. These small space rocks before they hit the atmosphere are called meteoroids. Once they enter the atmosphere and create that visible streak of light as they burn up, they are called meteors. And in the rare instance that a meteoroid is large enough to survive the fiery journey through the atmosphere and actually land on the Earth's surface, the piece that survives is then called a meteorite. So, a shooting star is really a meteor, the luminous trail left by a tiny meteoroid disintegrating high above us. Where do these little cosmic travelers come from? Most of the meteoroids that cause meteor showers are tiny fragments of dust and rock shed by comets as they travel through the solar system, leaving trails of debris in their wake. Other meteoroids can be small pieces broken off from asteroids in the asteroid belt or elsewhere. So, the next time you see a shooting star, remember you're witnessing the fiery end of a tiny piece of solar system history, not a star streaking across the cosmos. Here's a myth that comes up often, probably because of a popular song title and some compelling photos. The idea that the dark side of the moon is always dark. It sounds logical at first glance. If we always see the same face of the moon from Earth, maybe the other side is forever shrouded in shadow. But this is a classic misunderstanding of how the moon orbits and is illuminated by the sun. The term dark side is really a misnomer. What people are usually referring to is the far side of the moon, the hemisphere that never faces the Earth because the moon is tidally locked with our planet. Tidal locking means the moon's period of rotation on its axis is the same as its orbital period around Earth. So, as the moon orbits us, it spins, but in a way that keeps that one face pointed in our direction at all times. However, the moon is still orbiting the sun, just like Earth is. This means that both the near side, the side we see, and the far side, the side we don't see, experience sunlight. The moon has a day and night cycle just like Earth. It's just a much longer one. A lunar day from sunrise to sunset on the moon lasts for about 2 Earth weeks, followed by about 2 Earth weeks of lunar night. As the moon goes through its phases as seen from Earth, new moon, crescent, quarter, gibbous, full moon, different parts of the moon's surface, both the near and far sides, are being illuminated by the sun. When we see a new moon from Earth, it means the side facing us is in shadow, experiencing night, while the far side is fully illuminated by the sun, experiencing daytime. Conversely, during a full moon, the near side is bathed in sunlight while the far side is in darkness. So, the far side of the moon gets just as much sunlight as the near side. It's just never visible to us on Earth because of the moon's synchronized rotation and orbit. The only side of the moon that is always dark is the side that is currently facing away from the sun at any given moment, which changes constantly as the moon orbits. The dark side is a poetic phrase, perhaps, but the reality is that the far side of the moon experiences a full cycle of day and night, just out of our view from our vantage point on Earth. It's a whole other hemisphere, and thanks to missions like the Apollo program and robotic probes, we've been able to map and understand this hidden face of our closest celestial neighbor. Let's pivot from our lunar neighbor to the distant pinpricks of light that fill the night sky, the stars. When you look at a star, it's natural to think you are seeing it exactly as it appears at that very moment. But this leads us to another fascinating space myth, that we see stars as they are right now. The incredible reality is that when you gaze upon a star, you are essentially looking into the past. This is due to the absolutely vast distances involved in space and the finite speed of light. Light, while incredibly fast, doesn't travel instantaneously. It takes time for the light emitted by a star to cross the immense gulf of space and reach our eyes here on Earth. We measure these cosmic distances using a unit called a light year. A light year is not a measure of time, but a measure of distance, specifically the distance that light travels in 1 Earth year. That's about 9.46 trillion kilometers. So if a star is, say, 100 light years away, it means the light you are seeing from that star tonight began its journey 100 years ago. You are seeing that star as it was a century in the past. Consider some famous stars. Alpha Centauri, one of the closest star systems to our own, is about 4.37 light years away. This means the light you see from Alpha Centauri left that star system over 4 years ago. The North Star Polaris, which is essential for navigation, is much further, roughly 433 light years away. So, the light from Polaris that reaches us tonight started its journey around the time of Galileo Galilei. The bright star Betelgeuse in the constellation Orion is estimated to be around 640 light years away. If Betelgeuse were to explode as a supernova today, we wouldn't see that spectacular event for another 640 years. This concept also brings up a slightly unsettling thought. Some of the stars whose light we see in the sky tonight might actually no longer exist. If a star that's 1,000 light years away died 1,000 years ago, its light is just now reaching us, and we are seeing its final moments as if they were happening now. This cosmic time delay means the night sky is not a real-time snapshot of the universe, but rather a collection of images from different moments in the past, a truly humbling perspective on the scale of space and time. You know, we've already touched upon the idea that you can't hear explosions in space because sound needs a medium. This leads to another very common myth, the belief that space is completely silent, an absolute void where no sound of any kind exists. While it's true that sound waves, the kind we hear on Earth traveling through air, cannot propagate through the near vacuum of space, saying space is completely silent is an oversimplification and, in a way, a myth itself. While there's no air to carry traditional sound waves, space is far from being without activity that can be interpreted as sound with the right tools. Space is filled with various forms of energy and particles, including electromagnetic waves like radio waves and plasma waves, which are oscillations in ionized gas. These forms of energy do travel through the vacuum. Scientists can detect these waves and, using instruments, translate the variations in their frequencies and amplitudes into audible sound. It's not the same as hearing an explosion, but it allows us to listen to the dynamic processes happening in space. Think of it like this: a radio receiver takes electromagnetic waves and converts them back into the sound of someone talking or music playing. Space is broadcasting its own complex symphony, just not in the form of sound waves our ears can directly pick up. For example, spacecraft traveling through different regions of the solar system have recorded variations in plasma waves caused by the solar wind interacting with planetary magnetic fields. When scientists convert these variations into audio files, they produce often eerie, sometimes beautiful, and always fascinating sounds: whirring, whistling, crackling noises that give us a different sensory experience of the space environment. Jupiter's magnetosphere, or the region of space influenced by its magnetic field, is particularly known for producing complex radio emissions that, when converted to audio, sound surprisingly like whale songs or strange electronic music. Even events around black holes or neutron stars, while not producing audible booms in space, generate immense energy that can be detected as electromagnetic waves and studied. So, while you won't hear a sonic boom in the vacuum after a supernova, the space environment is rich with different forms of energy that scientists can transform into audible representations, revealing that the cosmos is not utterly silent, just silent in a way that requires a different kind of listening. When you picture Saturn, what comes to mind? For most of us, it's those magnificent rings, a defining feature that makes Saturn one of the most iconic planets in our solar system. And while those rings look incredibly solid and smooth in images, almost like a giant frisbee orbiting the planet, that visual leads to another common myth, that Saturn's rings are solid structures. The reality is far more complex and arguably even more amazing. Those stunning rings aren't solid at all. They are actually made up of billions, perhaps even trillions, of individual pieces of ice and rock, each orbiting Saturn independently. Imagine a colossal swarm of particles ranging in size from tiny dust grains, smaller than a speck of glitter, to chunks as large as houses or even small mountains. These countless particles are spread out over a vast area, forming thin, flat rings that stretch hundreds of thousands of kilometers from Saturn, but are only tens of meters thick in most places. What holds them in this incredible formation? It's Saturn's powerful gravity. Each particle is essentially a tiny moonlet following its own orbit around the planet, pulled by Saturn's immense gravitational force. As these particles orbit, they are constantly interacting with each other. They bump and nudge, creating a dynamic environment within the rings. Think of it less like a solid disk and more like a very, very crowded traffic jam where every vehicle is a piece of ice or rock. This constant interaction and collision among particles is what sculpts the rings into the familiar shapes we see. Looking closely at the rings reveals that they aren't just one solid band, but are actually composed of multiple distinct rings designated by letters like A, B, C, D, E, F, and G, separated by noticeable gaps and divisions. The most prominent gap is the Cassini division, a dark band between the A and B rings, which is wider than the planet Mars. These divisions and gaps aren't empty space. They are often areas where there are fewer particles, sometimes cleared out by the gravitational influence of Saturn's moons. Some of these moonlets, known as shepherd moons, orbit within or near the rings, and their gravity helps to shape and maintain the sharp edges of the rings and create specific divisions. The complex structure of Saturn's rings, with their intricate bands, gaps, and waves, is a testament to the gravitational ballet performed by countless small particles orbiting a giant planet. So, while they look solid from afar, those rings are really a colossal, dynamic collection of cosmic rubble. When you witness the breathtaking phenomenon of a total solar eclipse, it certainly looks like the moon is exactly the same size as the sun, perfectly covering its fiery disk. It's a spectacular alignment that creates a temporary twilight and allows us to see the sun's ethereal corona. This visual perfect fit often leads people to believe a popular myth that during an eclipse the moon is somehow bigger than the sun. But the truth behind this incredible celestial display is actually a mind-boggling cosmic coincidence involving vast differences in scale and distance. In reality, the sun is absolutely enormous compared to the moon. Our sun has a diameter of about 1.4 million kilometers. The moon, on the other hand, has a diameter of only about 3,474 kilometers. That means the sun is roughly 400 times wider than the moon. If the sun were the size of a basketball, the moon would be about the size of a pea. So clearly, the moon is not bigger than the sun. The reason the moon can appear to completely cover the sun during a total solar eclipse is because of its proximity to Earth compared to the sun's immense distance. While the sun is vastly larger, it's also about 150 million kilometers away. The moon is significantly closer, orbiting Earth at an average distance of about 384,000 kilometers. Because the moon is so much closer, its smaller size combined with that closer distance makes it appear from our perspective on Earth to be roughly the same size as the much larger, but also much more distant sun. Imagine holding a coin up to cover a distant building. The coin is obviously tiny compared to the building, but if you hold the coin at just the right distance from your eye, it can completely block your view of the much larger structure. A total solar eclipse is essentially this same effect, but on an astronomical scale, with the moon perfectly positioning itself between the Earth and the sun. The precision of this alignment, where the apparent size of the moon in the sky is almost exactly the same as the apparent size of the sun, is truly remarkable and is what makes total solar eclipses such a rare and stunning event. It's a demonstration of how perspective and distance play crucial roles in how we perceive the size of celestial objects. Building on our discussion of what doesn't happen in space, let's address another dramatic scenario often depicted in fiction. The idea that if you're exposed to the vacuum of space without a spacesuit, your body will instantly and violently explode. It's a terrifying thought, your body just bursting apart due to the lack of external pressure. But like many cinematic portrayals, this is a significant exaggeration of the scientific reality. While exposure to the vacuum of space is absolutely, unequivocally deadly and you would not survive for long, your body would not instantly detonate like a balloon bursting. Here's what would actually happen based on scientific understanding and some unfortunate historical accidents involving pressure loss at high altitudes. The most immediate and critical effect of being exposed to vacuum is the lack of oxygen. You would lose consciousness within seconds, perhaps 10 to 15, due to hypoxia, the severe lack of oxygen reaching your brain. This is the fastest killer. Simultaneously, the incredibly low pressure would cause the gases in your lungs and digestive tract to expand rapidly. This expansion would be very painful and could cause internal injury. Furthermore, bodily fluids like the water in your tissues and blood would begin to boil due to the low pressure, not because of heat, but because the boiling point of water decreases dramatically as pressure drops. This is similar to how water boils at a lower temperature at high altitudes on Earth. This boiling and vaporization of fluids would cause your body to swell considerably. However, your skin and circulatory system are elastic and strong enough to contain this swelling. They can withstand the internal pressure, preventing your body from literally exploding. Think of it like an extremely overinflated balloon. It gets bigger and bigger, but it won't necessarily explode instantly unless there's a defect or puncture. The lack of pressure would also lead to ebullition, the formation of gas bubbles within your bodily fluids, which would disrupt circulation and organ function. Beyond the immediate effects of pressure loss and lack of oxygen, you would also face the dangers of extreme temperatures, which we've touched upon. In direct sunlight, you'd be exposed to intense radiation and heating, while in shadow, you'd face extreme cold. However, as we discussed, heat loss through radiation is slow, so freezing solid would take time. You would also be exposed to various forms of radiation, including solar and cosmic rays, which are damaging to tissues. So, while being exposed to the vacuum of space is a swift and horrifying death due to asphyxiation, swelling, boiling of fluids, and rapid unconsciousness, the idea of your body spectacularly exploding is a myth. The reality is grim enough without the added Hollywood drama. We've talked about the dark side of the moon, which isn't always dark, but is there perhaps a dark side of the entire universe, a vast region where light simply doesn't exist? This idea might come from visualizing the empty spaces between galaxies and thinking of them as completely devoid of all radiation. However, the concept of a truly dark side of the universe in that sense is another myth, scientifically inaccurate. While space between celestial objects is incredibly empty compared to, say, a star or a planet, it's not a void without any form of light or radiation. One of the most profound pieces of evidence for this is the existence of the cosmic microwave background radiation, often abbreviated as CMB. This is a faint glow that permeates the entire universe, a relic from the very early universe, just a few 100,000 years after the Big Bang. At that time, the universe was a hot, dense plasma, full of energetic photons, light particles. As the universe expanded and cooled, these photons were released, and they've been traveling through space ever since. Due to the continued expansion of the universe, the wavelengths of this light have been stretched over billions of years, shifting from visible light and higher energies down into the microwave part of the electromagnetic spectrum, which is invisible to our eyes. But this faint microwave radiation is everywhere we look in the cosmos, coming from every direction. It's a subtle but constant bath of light left over from the universe's fiery dawn. So, even in the vast, seemingly empty spaces between galaxies, this primordial light fills the void. While these intergalactic spaces are indeed incredibly vast and contain very little visible light compared to the bright points of galaxies, they are not completely dark. There are also diffuse fields of starlight from distant galaxies and other forms of electromagnetic radiation like radio waves and X-rays traveling through the cosmos. The universe isn't divided into a light side and a dark side. Rather, it's filled with various forms of radiation, much of it invisible to us, a continuous cosmic tapestry of energy and particles, even in the deepest voids. Now, let's step into a topic that sparks endless fascination and debate, a myth that's probably kept many of us looking up at the night sky with hopeful or perhaps anxious eyes, the idea that aliens have already visited Earth. This isn't just a fringe belief. Polls show a significant portion of the population, believes that UFO sightings and other unexplained phenomena are evidence of extraterrestrial visitors. We see it everywhere in popular culture, from ancient astronaut theories to modern abduction narratives. The notion that advanced civilizations from other worlds have traveled vast distances to reach us is a powerful one. But here's where science steps in with a dose of cold, hard scrutiny. Despite countless claims, alleged sightings, and even purported encounters, there remains a critical absence of credible, verifiable scientific evidence to support the idea that aliens have actually visited our planet. When scientists talk about evidence, they mean something that can be independently observed, tested, and replicated, following the rigorous methods of scientific inquiry. Anecdotal accounts, blurry photographs, or witness testimony, while sometimes compelling stories, simply do not meet this standard on their own. Many alleged close encounters or UFO sightings can, upon investigation, be explained by natural phenomena or human-made objects. Weather balloons, conventional aircraft, satellites, atmospheric effects like unusual cloud formations, the planet Venus appearing exceptionally bright, or even simple optical illusions can all be misinterpreted as something extraterrestrial. Furthermore, while billions of dollars have been spent on radar systems, satellites, and telescopes designed to monitor our skies and space, none have ever provided conclusive proof of alien spacecraft visiting Earth. This isn't to dismiss the experiences people report, but to recognize that extraordinary claims require extraordinary evidence, and that evidence must stand up to scientific rigor. The scientific search for extraterrestrial life does exist, but it takes a different approach. Projects like SETI, the search for extraterrestrial intelligence, use radio telescopes to listen for artificial signals that might be broadcast by other civilizations, looking for evidence of technology, not visitation. Astrobiologists study extremophiles' life that thrives in extreme conditions on Earth to understand the potential range of environments where life might exist elsewhere. And astronomers search for exoplanets in habitable zones, planets orbiting other stars at a distance where liquid water could potentially exist on the surface. These are evidence-based approaches, focusing on detecting signs of life or intelligence from afar, rather than assuming visitation has already occurred. Encouraging critical thinking about alleged alien visits involves considering alternative explanations for unexplained sightings and understanding the difference between belief and scientific evidence. It's okay to wonder and speculate, but it's also important to evaluate claims based on whether they are supported by verifiable facts and rigorous investigation. The mystery of whether we are alone in the universe is one of the most exciting questions facing humanity, and while the possibility of alien life is real and actively being searched for by scientists, the myth of past or present alien visitation, as a well-documented fact, remains unsupported by the kind of evidence required by science. Here's a myth that sounds like it could be a fun perk of becoming an astronaut, that going to space will make you significantly taller, perhaps adding several inches to your height. While it's true that astronauts do experience a temporary increase in height during their time in space, the idea that it's a dramatic or permanent growth spurt is simply not accurate. The slight increase in height observed is a fascinating physiological adaptation to the microgravity environment. On Earth, gravity is constantly pulling down on our bodies, compressing our spines. The 70 vertebrae in our spinal column are separated by discs of cartilage, which act as shock absorbers. This constant gravitational force causes these discs to compress slightly over the course of the day, making us a little shorter in the evening than when we woke up. In the near weightless conditions of space, this gravitational compression is no longer present. Without the constant pull, the intervertebral discs in an astronaut's spine can expand and spread out slightly. This causes the spine to lengthen a bit, resulting in a small increase in overall height. This gain is typically modest, usually around an inch or two, about 2 to 5 centimeters for most astronauts, depending on how long they spend in space. It's certainly not a growth of several inches that would make you dramatically taller. Importantly, this change is entirely temporary. As soon as astronauts return to Earth and are once again under the influence of full gravity, their spines recompress and they quickly return to their original height. The disks return to their normal spacing and the slight lengthening reverses. The temporary height increase is just one of many physiological changes the human body undergoes in space due to the absence of gravity. Astronauts also experience bone density loss, muscle atrophy, changes in fluid distribution leading to the puffy-faced, skinny-legged look, and alterations in their cardiovascular system. These are all areas of intense study for space medicine researchers, as understanding and mitigating these effects is crucial for longer duration missions. So, while going to space does give you a brief moment of slightly extra stature, don't expect to need a new wardrobe when you get back down to Earth. Here's another common belief that's not quite accurate, perhaps fueled by images of frozen planets and the general emptiness of the cosmos, that space itself is always uniformly cold. The idea is that because there's nothing out there, it must be absolutely freezing everywhere. But temperature in space is actually a lot more complicated and varied than that, and it's definitely not uniform. The feeling of cold or hot is really about the presence of heat energy in matter. In the vacuum of space, there's no air or medium to hold warmth. So, if you're far away from any source of heat, like a star or a planet, the temperature of space itself is indeed incredibly low, getting down to just a few degrees above absolute zero. That's around -270 degrees Celsius. This is the temperature of the cosmic microwave background radiation we discussed earlier, the faint leftover heat from the Big Bang thinly spread across the universe. However, things change dramatically when you introduce a heat source, and the most significant heat source in our solar system is the Sun. If an object in space is in direct sunlight, it can get incredibly hot because it's constantly absorbing energy from the Sun's radiation. Think about how hot the surface of the Moon gets during its 2-week-long daytime, reaching over 120 degrees Celsius in direct sunlight. Conversely, if an object is in the shadow, shielded from the Sun's rays, it radiates its own heat away into the cold vacuum and can become extremely cold. The surface of the Moon on the night side drops to about -150 degrees Celsius. Without an atmosphere to act as an insulating blanket like Earth's does, there's nothing to trap heat or distribute it evenly. This is why objects in space experience extreme temperature swings depending on whether they are facing the Sun or are in shadow. Spacecraft, for example, face this constant challenge. One side of the spacecraft might be baking hot in direct sunlight, while the other side, facing away from the Sun, is approaching that extremely low background temperature. To cope with these wild temperature fluctuations and keep their sensitive equipment within operational limits, spacecraft use sophisticated thermal control systems. These systems can involve layers of insulating materials, reflective surfaces to bounce away sunlight, radiators to shed excess heat, and sometimes even internal heating units for components in perpetual shadow. So, while deep space far from any stars is very cold, the temperature an object experiences in space is highly dependent on its location and whether it's absorbing radiation from a nearby heat source. Space isn't uniformly cold, it's a place of extreme temperature contrasts. Picking up on our earlier discussion about the color of Mars and how images are sometimes enhanced, let's dive deeper into why the red planet is red. The common explanation is that it's simply covered in rust or iron oxide, and while that's a major factor, it's not the whole story. Thinking of Mars as just one big ball of rust is another simplification, a myth that doesn't capture the full picture of its surface composition. It's true that iron oxides are undeniably the main reason for the reddish color. The Martian surface is rich in iron-bearing minerals, and over billions of years, these minerals have reacted with oxygen, a process much like rusting here on Earth. This rust, or ferric oxide, is a finely powdered dust that covers much of the planet, giving it that pervasive red hue. But it's not just a uniform coating of identical rust. The color we see is also influenced by how incredibly fine this dust is and how it hangs in the Martian atmosphere. These tiny particles, suspended in the thin air, scatter sunlight in a way that makes the sky appear pinkish or salmon-colored from the surface and contributes to the reddish appearance seen from space. However, if you look closely at images of Mars from orbiters and rovers, you'll notice that the color isn't a single, unchanging shade of red everywhere. There are areas that appear more orange, some that are brownish, and even regions that are darker, grayer, or blackish. These variations in color are due to a few things. Firstly, while iron oxides are widespread, the concentration and specific type of iron oxide can vary in different locations. Secondly, the Martian surface is made up of various minerals and rocks, not just iron oxides. Different geological processes have exposed or created areas with different compositions. For instance, some rocks are basaltic, volcanic in origin, and appear darker or grayish. Other areas might have deposits of sulfates or chlorides, which can have different colors depending on their composition and hydration. Erosion, wind patterns, and impact events constantly churn and redistribute the surface materials, creating patches and layers with distinct appearances. So, while rust is definitely the dominant colorant, the overall reddish appearance of Mars is a result of the widespread iron oxide dust, its presence in the atmosphere, and the variations in other minerals and rock types exposed on the surface. It's a complex geological canvas, not just a uniformly rusted ball, and that complexity is part of what makes exploring Mars so scientifically exciting. Another intriguing myth often encountered, especially in visually driven science fiction, is that space is a completely static, unchanging void, existing solely as a backdrop against which cosmic events unfold. This perspective sees space as a mere stage, rather than an active participant in the universe's dynamics. However, thinking of space as passive and inert is a significant misunderstanding of modern physics. According to our best current understanding, space itself is not empty or static. It's a dynamic entity woven into the fabric of space-time. Einstein's theory of general relativity revolutionized our understanding of gravity by proposing that it's not just a force, but rather a curvature in the fabric of spacetime caused by mass and energy. Massive objects like stars and planets warp the spacetime around them, and this warping is what we perceive as gravity. This means that space isn't just a container. It's actively being stretched, bent, and distorted by the presence and movement of matter and energy. Beyond being influenced by gravity, space is also expanding. Observations of distant galaxies show that they are moving away from us, and the further away they are, the faster they are receding. This isn't because galaxies are moving through space like marbles rolling across a floor. Instead, it's space itself that is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon move further apart as the balloon expands. This expansion of space is a fundamental property of the universe on large scales, and it's not just happening out there. It's happening everywhere, though its effects are only noticeable over vast cosmic distances. Furthermore, the concept of quantum fluctuations touched upon earlier suggests that even in supposedly empty space, there's an underlying energy and activity at the quantum level, with particle-antiparticle pairs fleetingly appearing and disappearing. While these fluctuations are on incredibly tiny scales, they contribute to the idea that space is not truly nothingness. Space, therefore, is not just a passive void. It's a dynamic, expanding, and warpable entity that is intimately connected with time and plays an active role in the behavior of the universe. It's the stage and one of the main characters in the cosmic play. Continuing our journey through space myths, here's one that might seem logical at first glance, particularly for those who enjoy contemplating extreme scenarios. The idea that if you fell into a black hole, you would be instantly crushed into a tiny point. The image is often one of being squeezed like toothpaste into an infinitely small singularity. While the outcome of falling into a black hole is certainly fatal and involves unimaginable forces, the process of being crushed isn't instantaneous in the way some might imagine, and the nature of the forces depends greatly on the size of the black hole. For smaller, stellar mass black holes, those formed from the collapse of a single massive star, with masses up to a few dozen times that of our Sun, the tidal forces are incredibly strong very close to the event horizon. Tidal forces are the differential gravitational forces acting on different parts of an object. In the case of a black hole, the gravitational pull on your feet, if you were falling in feet first, would be significantly stronger than the pull on your head because your feet are closer to the black hole's center. This difference in gravitational pull would stretch your body vertically while compressing it horizontally, a process dramatically but accurately nicknamed spaghettification. For a stellar mass black hole, these tidal forces become lethal before you even reach the event horizon. So long before you cross the point of no return, you would be stretched and torn apart by the intense gravity gradient. However, the scenario changes dramatically when you consider supermassive black holes, the colossal black holes billions of times the mass of our Sun that reside at the centers of most galaxies, including our own Milky Way. Because the singularity of a supermassive black hole contains so much mass, the event horizon is much larger. This means that the tidal forces at the event horizon are much weaker than for a stellar mass black hole. While the gravity is still immensely strong, the difference in gravitational pull across your body as you cross the event horizon would be less significant. For a sufficiently large supermassive black hole, you could potentially cross the event horizon without being immediately spaghettified. What happens after crossing the event horizon is still a subject of intense scientific research and theoretical physics, but according to classical general relativity, you would continue to fall towards the singularity and eventually be crushed there. However, crossing the event horizon itself would not necessarily be an instant crushing, particularly for supermassive black holes. It's a journey past the point of no return into a realm where the laws of physics as we understand them in our everyday experience break down. So, while stellar mass black holes would spaghettify you before entry, falling into a supermassive black hole might offer a brief, terrifying, and ultimately fatal plunge across the event horizon before the inevitable. It's a far cry from instantaneous, uniform crushing. Let's examine a common phrase associated with the Sun, one that creates a mental image that isn't quite scientifically accurate, the idea of the Sun burning out. This expression suggests that the Sun is like a finite fuel source, perhaps a log in a cosmic fireplace, that will eventually be consumed and extinguished. While the Sun does have a finite lifespan and will eventually cease to produce energy in the way it does now, the term burning out is misleading because, as we've discussed, the Sun isn't burning through combustion. The Sun is powered by nuclear fusion, converting hydrogen into helium in its core. This process releases a colossal amount of energy, and the Sun has been doing this for about 4.6 billion years. It has enough hydrogen fuel in its core to continue this fusion for roughly another 5 billion years, so it's not going to run out of fuel anytime soon. When the Sun does eventually exhaust the hydrogen in its core, it won't just burn out and disappear. Instead, it will undergo dramatic transformations. The core will contract and heat up, causing the outer layers of the Sun to expand significantly. The Sun will swell up into a red giant star, becoming hundreds of times its current size, potentially engulfing the inner planets, including Earth. During this red giant phase, it will begin to fuse helium into heavier elements like carbon and oxygen. Eventually, after it has exhausted its helium fuel, the Sun doesn't have enough mass to fuse heavier elements. Its outer layers will be expelled into space, forming a beautiful shell of gas and dust called a planetary nebula. The remaining core will collapse into a dense, hot object called a white dwarf. A white dwarf is essentially the leftover ash of a star's nuclear furnace, and it no longer undergoes fusion. It slowly cools down over billions or trillions of years, radiating away its stored heat. Eventually, it will become a cold, dark stellar remnant, a black dwarf, though the universe is not yet old enough for any white dwarfs to have cooled into black dwarfs. So the Sun won't burn out like a fire going cold. It will evolve through different stages powered by different nuclear reactions, eventually ending its life as a white dwarf that slowly fades away. The phrase captures the idea of an end to its current life, but the physical processes involved are far more dramatic and complex than simple combustion. Here's a notion that often pops up in discussions or visualizations of space, that the Earth's atmosphere just abruptly ends at some specific altitude, like hitting a wall as you ascend from the surface. This idea might be fueled by the concept of the edge of space, often quoted as 100 kilometers up, known as the Kármán line. While this line is a useful marker for defining where aeronautics ends and astronautics begins, it doesn't represent a sudden drop-off in atmospheric particles. The truth is, Earth's atmosphere doesn't have a sharp boundary. It gradually fades away into the vacuum of space. The air molecules become progressively thinner and more spaced out the higher you go. Think of it like a gradient rather than a distinct edge. As you ascend through the layers of the atmosphere, the troposphere, stratosphere, mesosphere, thermosphere, and exosphere, the density of air decreases dramatically. At the Kármán line, the atmosphere is already extremely thin, but there are still enough air molecules to create some drag on spacecraft. Beyond the Kármán line, in the thermosphere and exosphere, the atmosphere continues to thin out. In the exosphere, which is the outermost layer extending potentially thousands of kilometers into space, particles are so far apart that they can travel long distances without colliding. Some particles in the exosphere eventually escape Earth's gravity and are lost to space, while others fall back down. This gradual thinning means that the transition from a breathable atmosphere to the near vacuum of space is a continuous process, not a sudden drop-off. Satellites in low Earth orbit, even at altitudes of several hundred kilometers, still experience some atmospheric drag, albeit very slight, which requires occasional boosts to maintain their orbits. The idea of a sharp edge to the atmosphere is a simplification. While the Kármán line serves as a practical boundary for different types of flight and spaceflight, the Earth's gaseous envelope gently dissipates into the interplanetary medium, a gradual transition rather than an abrupt end. It reminds us that many boundaries in the universe are not hard lines, but rather gradual shifts in conditions and properties. Moving on, let's tackle a myth that can sometimes cause confusion, especially when you hear about spacecraft going into orbit or escaping Earth's gravity. The misconception is that to get into space or orbit, a spacecraft needs to go straight up until it passes Earth's gravitational influence. This leads to the idea that escaping gravity is achieved simply by gaining enough altitude. However, achieving orbit or escaping gravity isn't just about getting high enough. It's fundamentally about achieving the right horizontal speed. Think back to our earlier discussion about the International Space Station being in a state of freefall around the Earth. A spacecraft achieves orbit not by getting beyond gravity's reach, which is impossible, as gravity extends infinitely, but by moving sideways so fast that as it falls towards Earth due to gravity, the Earth's surface curves away at the same rate. This requires tremendous horizontal velocity. To reach low Earth orbit, a spacecraft needs to achieve a speed of around 28,000 kilometers per hour. This is why rockets launch vertically initially, to get through the thickest part of the atmosphere quickly and efficiently. but they then pitch over and build up enormous horizontal speed parallel to the Earth's surface. It's this sideways speed that keeps them in orbit, constantly falling but never hitting the ground. To escape Earth's gravity entirely and travel to another planet or beyond the solar system, a spacecraft needs to reach an even higher speed, known as the escape velocity, which for Earth is about 40,000 kilometers per hour. At this speed, its trajectory becomes an open curve, and it will move away from Earth permanently, its forward momentum overcoming the continuous pull of gravity. Simply going straight up, even at high speed, wouldn't be enough to stay in space for long. Gravity would eventually pull it back down unless it achieved sufficient horizontal velocity. So, getting into space and staying there or leaving requires a delicate balance of altitude and, crucially, immense speed in the right direction. It's the speed, not just the height, that allows spacecraft to defy gravity's pull in the way they do. Here's a myth that sometimes arises when people think about interstellar travel, that if we could travel at the speed of light, we could instantly reach any point in the universe. The idea is that at light speed, time would essentially stop from the perspective of the traveler, making distances irrelevant. While traveling at speeds approaching the speed of light does have fascinating effects on time due to Einstein's theory of special relativity, reaching any point in the universe instantaneously is still a realm of science fiction, not scientific possibility as we currently understand it. Special relativity tells us that as an object with mass approaches the speed of light, its mass increases, its length contracts in the direction of motion, and time slows down for the object relative to a stationary observer. The faster you go, the more pronounced these effects become. If you could somehow travel exactly at the speed of light, time for you would indeed stop from the perspective of someone not moving at that speed. This is why photons, particles of light that do travel at the speed of light, don't experience time. From their perspective, their journey is instantaneous regardless of the distance. However, the critical point is that only particles with zero rest mass, like photons, can travel at the speed of light. Any object with mass, no matter how small, requires an infinite amount of energy to reach the speed of light. As an object with mass approaches the speed of light, its kinetic energy increases, and according to E equals mc squared, this increased energy is equivalent to an increase in mass. As the speed gets closer to the speed of light, the energy required, and thus the effective mass, approaches infinity, making it impossible to actually reach the speed of light. So, even if we had incredible propulsion technology, we would always be limited to traveling below the speed of light, while time would slow down for us as we traveled at relativistic speeds, allowing us to cover vast light years in a shorter amount of our subjective time compared to someone who stayed behind. The journey would still take time from the perspective of the universe at large. For example, traveling to a star 10 light-years away at 99.99% the speed of light would still take over 10 years from the perspective of Earth, even though for the traveler, perhaps only a few months might pass. Instantly traversing vast cosmic distances would require speeds exceeding the speed of light, which is currently considered impossible by the known laws of physics. Concepts like warp drives or wormholes that allow for faster-than-light travel are currently within the realm of theoretical physics and speculative science fiction, not proven capabilities. So, while near-light speed travel offers incredible possibilities for time dilation, it doesn't grant instantaneous travel across the universe. Moving into the realm of cosmic collisions, there's a dramatic image that often comes to mind when we think about galaxies interacting. Galaxies colliding head-on like two massive ships crashing in space, resulting in utter destruction. While galaxies do interact and collide, the process is far less like a head-on smash-up and much more of a gravitational dance and eventual merger. The myth is that galaxy collisions are destructive impacts that obliterate everything within them. The reality is that because galaxies are mostly empty space, direct collisions between stars within colliding galaxies are incredibly rare. Think back to the vast distances between stars within a galaxy. Even in the relatively crowded regions of our own Milky Way, stars are light years apart. When two galaxies collide, their vast stellar populations mostly pass through each other, with individual stars rarely, if ever, striking one another. The collision is instead dominated by the immense gravitational forces between the two galaxies. As they approach and pass through each other, their mutual gravity distorts their shapes, pulls out long streamers of stars and gas known as tidal tails, and triggers intense bursts of star formation due to the compression of gas clouds. The supermassive black holes at the centers of the galaxies can also interact, eventually merging into a single, even larger supermassive black hole. These galactic mergers are huge, drawn-out processes that take hundreds of millions or even billions of years to complete. The two galaxies pass through each other multiple times, their gravitational pulls slowing them down and drawing them closer with each pass until they eventually coalesce into a single, larger galaxy. The result of a galaxy collision isn't the destruction of both galaxies, but rather the formation of a new, often larger and differently shaped galaxy. Our own Milky Way galaxy is currently on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4.5 billion years, they will begin this process of gravitational interaction and merger, eventually forming a new, elliptical galaxy nicknamed Milkdromeda. This won't be a crash that destroys our solar system or sends stars scattering aimlessly. Rather, it will be a slow, majestic merging process driven by gravity, reshaping the cosmic landscape in our corner of the universe. Let's turn our attention back to our closest star, the Sun, and address a common misconception about its behavior. We often hear about solar flares and coronal mass ejections, and might picture the Sun as being constantly covered in violent eruptions, a perpetually chaotic surface firing off dangerous bursts of energy in all directions at all times. While the Sun is indeed a dynamic and active star that experiences powerful events, the myth is that these events are constant, uniform, and always directed at Earth. The Sun's activity follows an approximately 11-year cycle, known as the solar cycle, characterized by variations in the number of sunspots, solar flares, and coronal mass ejections (CME). During solar maximum, the peak of the cycle, these energetic events become much more frequent. During solar minimum, they are relatively rare, so the Sun's activity isn't constant, it ebbs and flows over time. Furthermore, when the Sun does have a flare or a CME, these events are localized phenomena originating from specific regions on the Sun's surface, often associated with sunspots, which are areas of intense magnetic activity. A solar flare is a sudden burst of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. A coronal mass ejection is a much larger expulsion of plasma and magnetic field from the Sun's corona, its outer atmosphere. These events are incredibly powerful, releasing vast amounts of energy. However, they don't happen uniformly across the entire solar surface at all times. And crucially, not every solar flare or CME is directed towards Earth. The Sun emits these bursts of energy and particles in various directions. Only when an event originates from a region on the Sun that is facing Earth, and the trajectory of the ejected material is aligned with our planet, do we experience the full effects. When a powerful CME is directed towards Earth, it can impact our planet's magnetic field and upper atmosphere, causing geomagnetic storms. These storms can lead to beautiful auroras visible at higher latitudes, but they can also disrupt radio communications, GPS signals, and even damage power grids and satellites. However, the Sun is not constantly bombarding us with these events. We have space-based observatories like the Solar Dynamics Observatory (SDO) that continuously monitor the Sun, allowing scientists to track solar activity, study these powerful events, and provide warnings when potentially Earth-directed storms are on their way. So, while the sun is indeed powerful and occasionally dramatic, it's not in a perpetual state of violent, Earth-directed eruption. Its activity is cyclical and often targeted, reminding us that even our closest star has its rhythms and variations. Let's address a powerful image often depicted in movies: a spacecraft experiencing intense shaking and turbulence as it travels through the vacuum of space, as if it's navigating through a stormy sea or a bumpy ride through the atmosphere. This visual is often used to create dramatic tension during maneuvers or when encountering cosmic phenomena. However, the reality is that travel through the vacuum of space is inherently smooth and involves none of the shaking or turbulence we associate with air travel or seafaring. Turbulence is caused by irregular fluid motion like air currents or water waves. In the near-perfect vacuum of space, there's no medium to create such turbulence. Once a spacecraft's engines are shut off, it travels through space at a constant velocity in a straight line or along a curved path dictated by gravity, which is a smooth influence, not a jerky one until acted upon by an external force. There's no friction from air, no currents to push against, and no resistance to its motion. Any shaking or vibration experienced within a spacecraft during normal flight would likely be due to internal factors, such as the operation of onboard machinery, the movement of astronauts, or perhaps slight structural flex. During engine burns or maneuvers using thrusters, the spacecraft will experience acceleration or deceleration, and potentially some vibration from the propulsion system. But once the engines are off, the ride becomes incredibly smooth. The only external factors that could cause a spacecraft to shake or change its orientation in a non-smooth manner are the firing of reaction-controlled thrusters for orientation adjustments, or potentially impacts from micrometeoroids or space debris, but these are impacts, not continuous turbulence. The dramatic shaking scene in movies of spacecraft flying through space is almost always added for dramatic effect, appealing to our terrestrial experience of motion. The silence and smoothness of actual space travel, while perhaps less visually exciting for a film, are a direct consequence of the vacuum environment. So, while the idea of weathering cosmic storms sounds exciting, the reality of coasting through the vacuum is a much calmer, albeit still challenging, form of travel. Thinking about the possibility of life beyond Earth often brings up the idea of the habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface of a planet. This concept is sometimes simplified into a myth that life can only exist within this specific zone, suggesting that any planet outside this range is automatically sterile. While the habitable zone is a crucial concept in astrobiology and a primary target in the search for exoplanets, the idea that it's the only place life can exist is too restrictive. The habitable zone, often called the Goldilocks zone, defines the region where a planet receives enough stellar radiation to keep water liquid on its surface, assuming a significant atmosphere. This is based on our understanding of the conditions necessary for life as we know it, which is heavily dependent on liquid water. However, the possibility of life existing in different environments, even outside the traditional surface habitable zone, is a growing area of scientific interest. Consider the subsurface oceans on moons like Europa and Enceladus within our own solar system, which are far outside the Sun's habitable zone based on their surface temperatures. As we discussed earlier, internal heating from tidal forces or radioactive decay can keep liquid water oceans warm beneath miles of ice. These subsurface oceans are shielded from the harsh radiation of space, offering potentially stable environments for life. Such deep, dark environments wouldn't rely on sunlight for energy in the way that life on Earth's surface does. Instead, they might be powered by chemosynthesis, using chemical energy released from hydrothermal vents on the seafloor, much like some ecosystems found at the bottom of Earth's oceans. Furthermore, the definition of the habitable zone itself is constantly being refined. Factors like the type of star, the composition and thickness of a planet's atmosphere, and geological activity all influence whether liquid water can exist. A planet with a thick, greenhouse gas-rich atmosphere could potentially retain enough heat to have liquid water on its surface, even if it's slightly further from its star than the traditional habitable zone boundary. And conversely, a planet closer to its star might still be habitable if it has a thin atmosphere and high reflectivity. So, while the habitable zone is a valuable framework for prioritizing the search for potentially Earth-like worlds, restricting the search for life only to this zone ignores other compelling possibilities, particularly those involving subsurface liquid water or life adapted to entirely different biochemical processes we haven't yet imagined. The universe is vast and diverse, and the potential abodes for life might extend far beyond our initial assumptions. Here's a myth that sometimes arises from simplified models and outdated information: that the asteroid belt between Mars and Jupiter is a solid, impassable barrier, a dense region packed so tightly with rocks that navigating through it is extremely difficult or even impossible. While we touched on this earlier when talking about asteroid belts not being like movie depictions, the myth specifically focuses on the idea of a solid-like barrier. The reality, as revealed by numerous spacecraft missions that have successfully traversed it, is that the asteroid belt is incredibly sparse. While it contains millions of asteroids, from tiny pebbles to dwarf planets like Ceres, these objects are spread out over an enormous volume of space. The average distance between significant-sized asteroids in the main belt is hundreds of thousands of kilometers. Imagine a vast ocean with only a few pebbles scattered across its surface. That's a more accurate representation of the asteroid belt's density than a solid wall of rocks. Spacecraft like Pioneer, Voyager, Galileo, Cassini, and New Horizons have all passed through the main asteroid belt on their journeys to the outer solar system without incident. They weren't dodging asteroids, they simply followed their trajectories through the vast, empty spaces between them. The primary risk to spacecraft traveling through the asteroid belt comes not from colliding with large asteroids, but from the possibility of hitting much smaller, untraceable dust particles or micrometeoroids, which can still cause damage at high speeds. However, even this risk is relatively low. The depiction of the asteroid belt as an impenetrable barrier is a dramatic exaggeration. While it is a region of space with a higher concentration of rocky bodies than surrounding areas, it is predominantly empty space. Understanding the true nature of the asteroid belt is important not only for dispelling myths, but also for future missions that might explore or even utilize its resources. It's a vast, mostly empty expanse, not a solid wall. Let's discuss a fundamental property of light and how it travels through the universe, addressing a myth that suggests visible light is somehow distinct from other forms of electromagnetic radiation, or that it travels differently. The myth might stem from the fact that visible light is what we can see with our eyes, making it seem special or separate from things like radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. However, all of these are simply different forms of electromagnetic radiation, and they all travel through the vacuum of space at the exact same speed, the speed of light. The only difference between these forms of radiation is their wavelength and frequency. Visible light is just a small portion of the full electromagnetic spectrum, the part that our eyes are sensitive to. Red light has the longest wavelength and lowest frequency in the visible spectrum, while violet light has the shortest wavelength and highest frequency. Beyond the visible red is infrared radiation, and beyond the visible violet is ultraviolet radiation. Even further out are radio waves, very long wavelengths, low frequencies, and gamma rays, very short wavelengths, high frequencies. Despite these differences in wavelength and energy, all electromagnetic waves are created by the oscillations of electric and magnetic fields and propagate through space at the speed of light. which is approximately 299,792,458 meters per second in a vacuum. This constant speed of light is a fundamental constant in physics and the cornerstone of Einstein's theory of special relativity. Whether it's the light from a distant star, radio signals from a spacecraft, or X-rays from a black hole, all these forms of electromagnetic radiation travel at the same breakneck speed through the vacuum of space. This is why we can use radio waves to communicate with distant probes, and why astronomers can study the universe across the entire electromagnetic spectrum. All the information transmitted by these different forms of light arrives at the same speed, carrying information about the cosmic processes that generated them. So, the concept of visible light being unique in its travel through space is a myth. It's just one part of a vast spectrum of radiation, all moving at the same ultimate speed limit of the universe. Here's a dramatic idea sometimes presented, that the Earth is in constant, imminent danger from falling asteroids, and that cosmic impacts are a frequent threat to life. While it's true that Earth is occasionally struck by objects from space, and major impact events have occurred throughout our planet's history, the myth is that catastrophic asteroid impacts are a regular occurrence that we are constantly on the verge of experiencing. The reality is that while small objects from space enter Earth's atmosphere every day, the truly large, civilization-threatening impacts are incredibly rare events on human timescales. Millions of small rocky and dusty particles hit Earth's atmosphere daily, most of them burning up completely as meteors, as we discussed earlier. Larger objects, like those that might cause damage on the ground, strike much less frequently. Objects large enough to cause regional devastation or even a global catastrophe, like the asteroid believed to have caused the extinction of the dinosaurs about 66 million years ago, are extremely rare. Scientists estimate that impacts from objects 1 kilometer or larger in diameter occur on average only once every few 100,000 years. Impacts from much larger objects, like the one that formed the Chicxulub crater and may have wiped out the dinosaurs, are estimated to occur only once every tens of millions of years. While these events are part of Earth's history and a genuine long-term concern, they are not a constant, immediate threat. Furthermore, scientists are actively working to identify and track near-Earth objects NEO, asteroids and comets whose orbits bring them close to Earth. Projects like NASA's Center for Near-Earth Object Studies (CNEOS) use telescopes and radar to find and monitor these objects, calculate their orbits, and assess any potential risk of impact in the future. The goal is to identify any potentially hazardous objects well in advance, giving us time to potentially deflect them if necessary. While the vastness of space means there are still many NEOs to be discovered, our ability to detect and track them is constantly improving. So, while the possibility of a future impact remains a scientific concern that warrants monitoring, the idea of Earth being under constant, imminent threat from asteroid impacts is an exaggeration of the actual risks based on current scientific understanding. It's more about long-term preparedness than daily panic. Let's explore another misconception related to gravity, specifically the idea that gravity is exactly the same everywhere on Earth's surface. You might assume that since the Earth is a sphere roughly, the gravitational pull would be uniform no matter where you are. However, the myth is that Earth's gravity is a constant, unchanging force across its entire surface. In reality, Earth's gravity varies slightly from place to place, and these variations, while small, are measurable and scientifically significant. Several factors contribute to these variations in gravitational acceleration, which is the force exerted by Earth's gravity on a given mass at a specific location. Firstly, the Earth is not a perfect sphere. It's an oblate spheroid, slightly bulging at the equator and flattened at the poles due to its rotation. Because the poles are slightly closer to the Earth's center of mass than the equator, gravity is slightly stronger at the poles than at the equator. Think of it as being a little closer to the source of the gravitational pull. Secondly, local variations in density of the Earth's crust and mantle affect gravity. Areas with denser rocks or larger subsurface masses will have a slightly stronger gravitational pull than areas with less dense material or cavities. Mountain ranges, deep ocean trenches, and even different types of geological formations all contribute to these local gravity variations. Altitude also plays a role. Gravity decreases slightly as you move further away from the Earth's center. So, gravity is weaker on top of a tall mountain than at sea level. Finally, the centrifugal force caused by the Earth's rotation also slightly counteracts gravity, particularly at the equator where this rotational effect is strongest. Scientists use instruments called gravimeters to measure these subtle variations in gravity. These measurements are not just scientific curiosities. They are used for various purposes, including geological surveys, mapping subsurface structures, and even in satellite navigation systems for precise positioning. The study of these gravity variations gives us valuable information about the Earth's interior structure and composition. So, while the differences are small compared to the overall gravitational pull, Earth's gravity is not perfectly uniform. It's a dynamic force with subtle variations across its surface, revealing the intricate nature of our planet's mass distribution. Engaging with the concept of black holes again, there's a particularly vivid and terrifying myth that persists: that black holes are permanent, unchanging cosmic prisons from which nothing, not even light, can ever escape, and that once something falls in, it is simply gone forever, contributing to the black hole's mass but otherwise having no further interaction with the universe. This idea of a black hole as an eternal one-way trap is challenged by a groundbreaking theoretical prediction by the famous physicist Stephen Hawking. Hawking proposed that black holes are not entirely black and that they can actually emit radiation, a phenomenon now known as Hawking radiation. According to quantum mechanics, even in the vacuum near the event horizon of a black hole, pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence and immediately annihilating each other. Near the event horizon, it's possible for one particle of a pair to fall into the black hole while the other escapes into space. From the perspective of an observer far from the black hole, it appears as though the black hole is emitting a faint stream of particles, which is Hawking radiation. This process means that black holes aren't just passively absorbing matter, they are also slowly losing mass and energy through this radiation. The rate of Hawking radiation is incredibly slow for stellar mass and supermassive black holes, so slow that they would take an unimaginably long time, far longer than the current age of the universe, to evaporate completely. However, for much smaller, theoretical, mini black holes that might have been formed in the early universe, the rate of evaporation would be much faster. As a black hole loses mass through Hawking radiation, its event horizon shrinks and the rate of evaporation increases. Eventually, a black hole that isn't consuming more matter than it's radiating away will theoretically evaporate entirely in a final burst of energy. This prediction is a complex area of theoretical physics at the intersection of quantum mechanics and general relativity, and directly detecting Hawking radiation has been incredibly challenging. However, the theoretical framework suggests that black holes are not completely permanent and unchanging. They have a temperature, and they can lose mass over time through this quantum process. This challenging of the myth of black holes as eternal, passive prisons is one of the most profound insights into the nature of these enigmatic cosmic objects. Let's consider another common misconception, often seen in visuals of planets like Earth with swirling clouds, that planetary atmospheres are simply passive, static layers of gas that just sit on the surface. This view overlooks the incredibly dynamic and constantly moving nature of atmospheres. Thinking of an atmosphere as static is a myth. Planetary atmospheres are vibrant systems driven by energy from stars and internal planetary processes, leading to complex weather and climate patterns. Earth's atmosphere, for example, is constantly in motion. Solar radiation heats the atmosphere unevenly, creating temperature differences that drive convection currents, leading to winds. The rotation of the planet influences these winds, creating large-scale circulation patterns like the jet streams and trade winds. Water vapor in the atmosphere contributes to weather phenomena like clouds, precipitation, and storms, powered by the release of latent heat. Even without liquid water, other planetary atmospheres show dynamic behavior. Jupiter's atmosphere is a prime example, characterized by persistent, swirling bands of clouds and enormous storms like the Great Red Spot, which has raged for centuries. These dynamics are driven by internal heat from Jupiter and its rapid rotation, creating complex atmospheric flows and turbulence. Mars, despite having a much thinner atmosphere than Earth, still experiences significant atmospheric activity, including global dust storms that can obscure the entire planet. Even on seemingly quiet worlds like Titan, Saturn's largest moon, the thick atmosphere of nitrogen and methane experiences weather, including methane rain and the formation of clouds. The movement and behavior of planetary atmospheres are governed by principles of fluid dynamics, thermodynamics, and radiative transfer, influenced by the planet's composition, rotation rate, presence of liquids or ices, and the amount of energy it receives. Studying these atmospheric dynamics is crucial for understanding a planet's climate, weather, and potential for harboring life. So, far from being static blankets of gas, planetary atmospheres are active, constantly moving systems that shape the surfaces below and play a vital role in the overall character of a world. Moving on to a concept often used to explain cosmic distances and the size of the universe, there's a myth that can emerge from the term itself, that the observable universe represents the entire universe, that everything outside of what we can see simply doesn't exist. The concept of the observable universe refers to the portion of the universe that we can see from Earth right now, given the age of the universe and the speed of light. Light from objects beyond a certain distance hasn't had enough time to travel across the expanding space and reach us since the Big Bang. The furthest light we can detect is the cosmic microwave background radiation, the light from the universe when it was only about 380,000 years old. The distance to the edge of this observable region is currently estimated to be about 46.5 billion light-years in every direction. This doesn't mean the universe ends there. The universe is likely much, much larger than the observable part, and it might even be infinite. We simply cannot see anything beyond that cosmic horizon because the light hasn't reached us yet, and in many cases, the space between us and incredibly distant regions has expanded faster than light could travel across it since the beginning of the universe. Imagine being on a ship in the middle of a vast ocean with a limited range of vision. You can only see the part of the ocean up to the horizon, but you know the ocean extends far beyond that. Similarly, the observable universe is our cosmic horizon, the limit of what's visible to us from our current location and time. The myth comes in when people equate this observable portion with the entirety of existence. The universe could contain countless galaxies, structures, and phenomena beyond our current ability to detect or observe. Cosmological models based on the Standard Model of Cosmology and the observed flatness of the universe suggest that the universe as a whole extends far, far beyond the observable horizon, potentially infinitely in extent. So, while the observable universe is incredibly vast and contains billions of galaxies, it is likely just a tiny fraction of the entire universe. There is a universe beyond what we can see, and its full extent remains one of the biggest mysteries in cosmology. Here's a common misconception, often perpetuated by visuals, that space is simply black and featureless between stars and galaxies. While it's true that the vast stretches of space between luminous objects can appear very dark, the idea that it's completely empty and devoid of any visual structure is a myth. Space isn't just black, it's a profound darkness punctuated by light, and it also contains diffuse material that, while not brightly lit, can be visible under the right circumstances. As we discussed earlier, the space between stars within a galaxy contains the interstellar medium, composed of gas, mostly hydrogen and helium, and dust grains. While this material is extremely diffuse compared to the air we breathe, it's not completely invisible. Under certain conditions, particularly near bright stars or when illuminated by background light, these clouds of gas and dust can be seen as nebulae, vast, often beautiful, clouds of glowing or dark material. Emission nebulae, like the Orion Nebula, glow because the gas within them is heated and ionized by nearby young, hot stars. Reflection nebulae scatter the light of nearby stars, appearing bluish. Dark nebulae, like the Horsehead Nebula, are dense clouds of dust that block the light from background stars, appearing as silhouettes against the brighter parts of the Milky Way. These nebulae, which can span hundreds or even thousands of light years, are striking visual features within our galaxy and other galaxies, showing that the space between stars is not simply empty blackness. Even the space between galaxies is not an absolute void, containing the extremely tenuous intergalactic medium and being permeated by the cosmic microwave background radiation. While this radiation is invisible to our eyes, it fills all of space. So, while the overwhelming impression of space is its darkness, it is far from being featureless or completely empty. It contains the diffuse remnants of star formation, the raw materials for future generations of stars and planets, and the faint afterglow of the Big Bang, all contributing to a cosmic environment that is much richer and more complex than simple blackness. Moving to another myth related to size and distance, there's a notion that can arise from looking at images of nebulae or star-forming regions, that these celestial clouds of gas and dust are relatively small and compact. We see them pictured within a frame, and it's easy to think of them as localized, perhaps roughly the size of our solar system. However, the reality is that many nebulae are absolutely colossal structures, spanning immense distances that dwarf the scale of our entire solar system. The myth is that nebulae are small cosmic clouds. The truth is, they are often vast interstellar structures. For example, the Orion Nebula, one of the most famous and easily observed nebulae in the night sky, is estimated to be about 24 light-years across. To put that into perspective, our solar system, out to the orbit of Neptune, is only about 6 light-hours across the time it takes light to travel from the Sun to Neptune. A light-year is over 9 trillion kilometers. So, the Orion Nebula is truly enormous, a region of gas and dust that is hundreds of thousands of times larger than our solar system. Other nebulae are even larger. The Lagoon Nebula is estimated to be about 52 light-years across, and the Carina Nebula is even larger, stretching hundreds of light-years. These nebulae are the birthplaces of stars, vast reservoirs of gas and dust that collapse under their own gravity to form new stellar systems. The intricate shapes and structures we see within them, sculpted by the radiation and stellar winds from young, massive stars, are happening on scales that are almost unimaginable from our everyday experience. So, while they might appear as contained clouds in images, nebulae are titanic cosmic nurseries, vast regions of the interstellar medium, reminding us of the incredible scale of processes happening within our galaxy and beyond. They are far from being small, compact clouds. Here's a common misconception, perhaps influenced by how we see celestial objects represented in diagrams, that planets and moons are just perfectly smooth, round balls. While many planets and moons are roughly spherical due to their own gravity pulling material towards the center, the idea that they are perfectly smooth is a myth. Most solid celestial bodies have incredibly varied and often dramatic surface features. Earth, of course, is a prime example, with its towering mountain ranges, deep ocean trenches, vast plains, and countless other geological formations. These features are all deviations from a perfect sphere. Our moon also has a heavily cratered surface, scarred by billions of years of impacts, as well as mountains, valleys, and lava plains. Even planets that appear relatively smooth from afar have surface topography. Mars has immense volcanoes, some larger than any on Earth, like Olympus Mons, as well as vast canyons like Valles Marineris, which is far larger than the Grand Canyon. Its surface is also covered in impact craters of various sizes. Mercury, the innermost planet, is also heavily cratered and has vast plains formed by ancient volcanic activity. Icy moons in the outer solar system, like Europa and Enceladus, while appearing relatively smooth in some areas due to their icy crusts, still have complex surface features like cracks, ridges, and evidence of past geological activity. The shape of celestial bodies is determined by a balance between the pull of gravity, which tends to make them spherical, and the strength of the material they are made of, which can support deviations from a perfect sphere. Smaller objects like asteroids and smaller moons have weaker gravity and less internal strength, so they are often irregularly shaped, not at all spherical. Only objects with sufficient mass to overcome their material strength and pull themselves into a roughly spherical shape are considered planets or dwarf planets. But even these large, massive bodies have surfaces marked by geological processes, impacts, and other forces that create a diverse and often rugged landscape, far from the idealized smooth spheres depicted in some illustrations. Concluding our exploration of space myths, let's address a powerful and often inspiring notion: that humans are completely unique in the universe, the pinnacle of evolution, and that our existence is somehow set apart from the rest of the cosmos. This isn't a scientific myth in the sense of being a falsifiable claim about the physical universe, but rather a philosophical idea that runs counter to our scientific understanding of our place in the cosmos. The myth is that humanity is fundamentally separate from the rest of the universe. The scientific reality, supported by decades of research in astronomy, physics, chemistry, and biology, shows that humans are an integral part of the universe, made of the very same stuff as stars and galaxies, and governed by the same fundamental laws of nature. The atoms that make up our bodies, the carbon, oxygen, nitrogen, iron, and all the other elements, were forged in the scorching hot cores of stars, often in massive stars that ended their lives in spectacular supernova explosions, scattering these elements across the galaxy. We are quite literally star stuff, the processes that led to the formation of our solar system, the emergence of life on Earth, and the evolution of complex organisms, including humans, are all natural processes that occurred within the framework of the universe's laws. While humanity has achieved remarkable feats in science, technology, and culture, our intelligence and consciousness, as far as we understand them scientifically, are the result of complex biological processes that arose through billions of years of evolution on one particular planet. There's no scientific evidence to suggest that these processes couldn't occur elsewhere in the universe under similar conditions. Our growing understanding of the vastness of the universe, the sheer number of stars and planets, and the potential for diverse environments, makes it increasingly plausible that the conditions necessary for life, and perhaps even intelligent life, could arise elsewhere. While we currently have no proof of life beyond Earth, the scientific perspective places humanity not apart from the cosmos, but firmly embedded within it, a product of its evolutionary processes and made of its fundamental constituents. This scientific view is not diminishing. Rather, it's a profound realization of our connection to the universe, a humbling perspective that highlights both our place within the grand scheme of things and the incredible journey of cosmic evolution that led to our existence. Understanding these scientific realities about space and our place in it replaces myths with a deeper, more awe-inspiring appreciation for the universe. When you look up at the night sky, often the first star people learn about is the North Star, also known as Polaris. It sits almost directly above the Earth's North Pole, making it an incredibly reliable guide for navigation. This prominence in the sky leads many to believe another popular myth, that the North Star is the brightest star we can see. While Polaris is certainly easy to find and holds significant importance because of its position, it is far from being the most luminous star visible from Earth. If you were to rank the stars in our night sky by their apparent brightness as seen from Earth, Polaris would typically land somewhere around the 48th brightest star. Its moderate brightness is often surprising to people who have been told their whole lives it's the brightest. Stars like Sirius, found in the constellation Canis Major, absolutely dominate the night sky in terms of apparent brightness. Sirius is so bright that it's often the first star you notice as twilight fades. Other stars like Canopus, the second brightest star visible from Earth, though not easily seen from most of the northern hemisphere, and Alpha Centauri, a star system in the southern hemisphere, are also significantly brighter than Polaris. So why does Polaris seem so important and relatively bright? It's all about location, location, location. Polaris's true value for navigation lies in its almost fixed position in the northern sky. As the Earth rotates, most stars appear to move across the sky from east to west, tracing arcs. But because Polaris is located nearly directly above the Earth's north celestial pole, the point in the sky that aligns with our planet's rotational axis, it appears to stay almost stationary throughout the night. All other stars in the northern hemisphere seem to revolve around it. This makes Polaris an invaluable tool for finding direction. Facing Polaris means you are facing north, and its height above the horizon can tell you your latitude. So, its importance isn't due to its stellar brilliance, but its unique celestial alignment, making it a dependable anchor in the moving tapestry of the night sky, a faithful guide through the darkness, even if much brighter stars shine elsewhere. Thinking about gravity on different planets, you might wonder if the rules of physics change depending on where you are in the solar system. Perhaps gravity works one way on Earth and a completely different way on Mars or Jupiter. This leads to a common myth that gravity itself works differently on different planets. But here's a fundamental concept in physics that's been proven time and again. The laws of gravity are universal. They apply everywhere in the cosmos, from the smallest moon to the largest galaxy. What does change from planet to planet isn't the law of gravity, but the strength of the gravitational pull you experience on that planet's surface. This strength depends on two main factors: the planet's mass and its radius. Sir Isaac Newton first described gravity as a force of attraction between any two objects with mass, a force that gets stronger with more mass and weaker with greater distance. Albert Einstein later refined our understanding with his theory of general relativity, explaining gravity as the curvature of spacetime caused by mass and energy, but the fundamental concept that mass creates gravity remains. The reason gravity feels stronger on one planet than another is simply because of how much stuff, mass, that planet contains and how far away you are from its center when standing on its surface, its radius. A more massive planet will exert a stronger gravitational pull. However, if that massive planet is also very large in diameter, you are further away from its center of mass when standing on the surface, which weakens the pull according to the inverse square law. Gravity decreases with the square of the distance. So, it's the combination of mass and radius that determines the surface gravity. Scientists talk about this as gravitational acceleration, the rate at which an object accelerates towards the surface of a planet due to gravity, or roughly how much you weigh. On Earth, the gravitational acceleration is about 9.8 meters per second squared. This means if you drop something, it speeds up by 9.8 meters per second every second it falls, ignoring air resistance. Because the gravitational acceleration is different on other planets, your weight, which is a measure of the force of gravity pulling on your mass, would also be different. Your mass, the amount of matter in your body, stays the same no matter where you are, but your weight changes with the local gravity. For example, if you weigh 150 pounds on Earth, you would weigh only about 57 pounds on Mars because Mars has less mass than Earth and a similar density, resulting in a weaker gravitational pull at its surface. On Jupiter, which is incredibly massive, you would weigh over 350 pounds, more than double your Earth weight, because Jupiter's immense mass creates a much stronger gravitational pull, even though you're standing on its cloud tops relatively far from its core. On the Moon, with its much smaller mass, that same 150-pound person would weigh a mere 25 pounds. So, while the force of gravity itself follows the same rules everywhere, the effective strength we feel on a planet's surface varies greatly depending on its physical properties, which is why jumping on the Moon looks so different than jumping on Earth. Let's tackle a concept that's fundamental to our understanding of the universe's origins, but is often misunderstood: the Big Bang. You might hear it described as a colossal explosion that happened in space, sending matter hurtling outwards into a pre-existing void. This idea paints a picture of a central point where everything began, with the universe expanding like shrapnel from a bomb. However, that dramatic image, while intuitively appealing, isn't scientifically accurate and constitutes another significant space myth. The Big Bang wasn't an explosion located within space, it was the rapid expansion of space itself. Imagine, if you can, a time when the entire observable universe, all the galaxies, stars, planets, and everything else, was compressed into an incredibly hot, dense state, smaller than a single atom. The Big Bang was the moment when this state began to expand, carrying all of space, time, and matter with it. There was no outside for it to explode into, because space as we know it was part of that initial incredibly dense state. It's like thinking about a balloon. If you draw dots on the surface of a deflated balloon to represent galaxies, and then you inflate the balloon, the dots move further away from each other not because they are traveling across the balloon's surface, but because the surface itself, the space between the dots, is stretching. In this analogy, the surface of the balloon represents the expanding space of the universe. There's no center point on the balloon's surface from which all the dots are moving away. Every dot sees all the other dots receding from it as the surface expands. Similarly, every point in the universe today sees all other distant points moving away, a direct consequence of the ongoing expansion of space. This expansion began rapidly in the early moments after the Big Bang, a period often referred to as inflation, and continues today, though at a more measured pace. Our understanding of the Big Bang isn't just theoretical, it's supported by compelling evidence. One of the strongest pieces is the cosmic microwave background radiation, which we touched upon earlier. This faint, uniform glow detected throughout the universe is the leftover heat from that incredibly hot, dense initial state, a direct echo of the Big Bang itself. Another key piece of evidence is the redshift of distant galaxies. When astronomers observe light from galaxies far away, they find that the wavelengths of this light are stretched towards the red end of the spectrum, a phenomenon called redshift. This redshift is interpreted as a Doppler effect caused by the galaxies moving away from us. And the further away a galaxy is, the greater its redshift, meaning it's receding faster, exactly what you would expect in a universe where space itself is expanding, carrying the galaxies apart. So, the Big Bang wasn't an event that happened in a pre-existing space. It was the beginning of space, time, and the universe we inhabit. A process of rapid and ongoing expansion from an incredibly hot and dense origin point. It's a concept that fundamentally changes how we think about the beginning of everything visible and tangible in the cosmos. For decades, if you asked someone how many planets are in our solar system, the answer was a confident 9: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But then, something changed, sparking a surprisingly passionate debate among scientists and the public alike, leading to a widespread myth that Pluto was somehow demoted unfairly. The truth is a bit more nuanced, and it revolves around our evolving understanding of the cosmos and what defines a planet. For many years, Pluto was considered the 9th and outermost planet. However, as astronomers developed better telescopes and detection methods, they began finding more and more objects in the outer solar system beyond Neptune in a region called the Kuiper Belt. These objects were icy and rocky, similar in composition to Pluto. The turning point came with the discovery of Eris in 2005. Eris is another Kuiper Belt object, and early estimates suggested it was even more massive than Pluto. This discovery forced astronomers to confront a critical question. If Eris was larger than Pluto, should it also be considered the 10th planet, or did the definition of planet need to be reconsidered? Recognizing the need for clearer criteria, the International Astronomical Union, or IAU, took on the task of defining what constitutes a planet in 2006. After much discussion and debate, they established 3 criteria for a celestial body to be classified as a planet within our solar system. First, it must orbit the Sun. Second, it must be massive enough for its own gravity to pull it into a nearly round shape. Pluto meets both of these criteria. The third criterion, however, was the sticking point for Pluto. A planet must have cleared the neighborhood around its orbit. This means that it must be the dominant gravitational force in its orbital path, having either accreted or ejected most other objects of similar size from that region over cosmic time. Pluto, residing within the crowded Kuiper Belt, simply does not meet this third criterion. Its orbit is populated by many other icy bodies, and it hasn't gravitationally cleared this region. This is the primary reason why the IAU reclassified Pluto as a dwarf planet. Other objects that meet the first 2 criteria but not the third, like Ceres in the asteroid belt and Eris, Haumea, and Makemake in the Kuiper Belt, are also classified as dwarf planets. This reclassification wasn't about diminishing Pluto's importance or scientific interest. It was about creating a more consistent and scientifically robust classification system for the growing number of objects we were discovering in the solar system. The current classification system now includes planets, the 8 worlds that cleared their orbits, dwarf planets like Pluto, Ceres, and Eris, and small solar system bodies, all other objects orbiting the Sun, such as asteroids and comets. While there are still some debates within the scientific community about the nuances of this definition, particularly the clearing the orbit criterion, the IAU's classification provides a clearer framework for understanding our solar system's diverse population. So, while the number 9 might be nostalgic, the scientific reality is that our solar system is home to 8 planets and a growing number of fascinating dwarf planets, a reflection of our ever-improving ability to explore and categorize the celestial bodies around us. We've talked about asteroid belts not being dense death traps, but let's zoom in on a single, incredibly significant asteroid impact. The story of the dinosaur extinction is etched into popular culture. A massive asteroid slams into Earth, causing devastation that ends the reign of these giant reptiles. This event, centered around the Chicxulub impactor that struck the Yucatan Peninsula about 66 million years ago, leads to a common myth that the asteroid that killed the dinosaurs was the biggest one to ever hit our planet. While the Chicxulub impact was undeniably catastrophic for life on Earth, it wasn't necessarily the largest asteroid impact event in our planet's deep geological history. Evidence hidden beneath the surface tells a different story. Scientists have identified impact structures around the globe, remnants of ancient collisions. One of the strongest candidates for a larger impact than Chicxulub is the Vredefort crater structure in South Africa. While the original crater is heavily eroded, geological evidence suggests that the impactor that created it, roughly 2 billion years ago, was estimated to be significantly larger than the Chicxulub object, perhaps 10 to 15 kilometers in diameter compared to Chicxulub's estimated 10 kilometers. The resulting crater structure was originally estimated to have been over 300 kilometers in diameter, making Vredefort the largest confirmed impact structure on Earth. Although the impact that created Rutherford was immense, the forms of life present on Earth back then were microscopic, so it didn't trigger a mass extinction event in the same way as Chicxulub. It's important to understand that the impact's consequences aren't solely determined by the size of the asteroid. Other factors play crucial roles. The composition of the impactor matters. For example, hitting a region rich in sulfur-bearing rocks, as was the case with Chicxulub, released enormous amounts of sulfur dioxide into the atmosphere. The location of the impact is also critical. The Chicxulub impact struck a shallow marine environment containing vast deposits of sulfates and carbonates. The immense energy of the impact vaporized these rocks, injecting massive quantities of sulfur dioxide, carbon dioxide, and other gases into the atmosphere. The sulfur dioxide reacted with water vapor to form sulfuric acid aerosols, which blocked sunlight, causing a dramatic global cooling event known as an impact winter. This disruption of the climate, along with widespread wildfires, tsunamis, and acid rain, was devastating to ecosystems worldwide, leading to the mass extinction that wiped out the non-avian dinosaurs and many other species. While the Rutherford impactor might have been larger, hitting a different type of terrain at a different point in Earth's evolutionary history led to different outcomes. So, while Chicxulub wasn't the largest impactor to ever strike Earth, its specific characteristics and the geological environment it hit made it uniquely devastating for the life forms present at that time. Here's a myth that often surfaces during discussions about government spending and priorities: the idea that space exploration is a luxurious waste of money, diverting precious resources that could be better spent on solving problems here on Earth like poverty, healthcare, or climate change. At first glance, it might seem like sending rockets and probes into the vastness of space is an expensive hobby compared to addressing immediate human needs. However, this perspective overlooks the profound and tangible ways that space exploration benefits life right here on our planet, making it less of a cost and more of an investment. Think about some technologies you use every single day. Your smartphone relies on satellite communication to connect calls and access the internet. When you use a GPS app to navigate, you're tapping into a network of satellites orbiting Earth. Precise weather forecasting, crucial for everything from agriculture to disaster preparedness, is made possible by sophisticated weather satellites. These are not fringe benefits. They are integral parts of our modern infrastructure, developed initially through the push and innovation required for space programs. The miniaturization of electronics, advancements in solar power, and even materials used in everyday products owe a debt to the need for lightweight, durable, and efficient technologies for spacecraft. The development of memory foam, for instance, originally created to absorb shock in aircraft seats, found widespread use after NASA funded its development for astronaut comfort and safety. Beyond technological spin-offs, the challenges of space exploration have spurred innovations with direct applications in medicine. The need to monitor astronauts' health remotely and in challenging environments has led to advancements in telemedicine and portable medical devices. Research conducted in the microgravity environment of the International Space Station has provided insights into bone density loss and protein crystal growth, potentially leading to new treatments for osteoporosis and diseases on Earth. The complex life support systems needed for spacecraft have driven innovation in water purification and air filtration technologies, with potential applications for providing clean water and air in challenging environments globally. Furthermore, engaging in the ambitious pursuit of exploring the cosmos inspires generations of young people to pursue careers in science, technology, engineering, and mathematics STEM. The wonder of space ignites curiosity, encouraging critical thinking and problem-solving skills that are essential for tackling Earth's challenges as well as venturing to other worlds. The pursuit of understanding the universe drives fundamental research that expands our knowledge and capability in ways we might not initially foresee. While the upfront costs of space missions are significant, the return on investment in terms of technological advancement, medical breakthroughs, economic growth from new industries, and educational inspiration is substantial and far-reaching. Framing space exploration as solely a cost ignores the immense value it creates for society and the critical role it plays in advancing human capability and understanding, not just of the cosmos, but of ourselves and our home planet. We've touched on the speed of light as a fundamental constant, the ultimate speed limit for electromagnetic radiation. But when we think about traveling amongst the stars, a persistent myth emerges that the speed of light is an absolute, unbreakable barrier for any kind of travel, especially for things we might build like starships. While it's true that according to the established laws of physics, specifically Einstein's special relativity, absolutely nothing with mass can reach or exceed the speed of light, the fascinating part of this myth lies in the creative ways scientists and thinkers explore the possibility of faster-than-light travel, not by breaking the speed limit ourselves, but by potentially changing the rule of the road, so to speak. Our current understanding tells us that as an object with mass accelerates, its energy increases, and as it approaches the speed of light, the energy required to accelerate it further approaches infinity. This means it's physically impossible for anything with mass to ever reach the speed of light. It's a fundamental limit woven into the fabric of space-time. However, this doesn't necessarily shut the door on the idea of traversing vast cosmic distances in a practical amount of time. Enter the realm of theoretical physics and concepts like warp drives. These aren't devices that propel a spacecraft through space at faster-than-light speeds in the conventional sense. Instead, theoretical models such as the Alcubierre drive proposed by physicist Miguel Alcubierre suggest a way to manipulate spacetime itself. Imagine being able to contract space in front of your spacecraft and expand it behind you, creating a kind of warp bubble. Within this bubble, the spacecraft itself would remain at rest or move at sublight speeds relative to the local spacetime inside the bubble. But because spacetime outside the bubble is being distorted, the bubble, and thus the spacecraft within it, could effectively travel from one point to another faster than light could travel the same distance through normal, undistorted space. It's crucial to emphasize that these concepts, while mathematically intriguing within the framework of general relativity, are currently highly speculative. They require exotic forms of matter or energy with properties we don't currently understand or know how to create, such as negative mass or energy density. Building a functional warp drive is vastly beyond our current technological capabilities, and there are significant theoretical hurdles and paradoxes that need to be addressed. So, while the speed of light remains the speed limit for objects moving through space, the possibility of manipulating space itself to achieve faster-than-light travel remains a captivating area of theoretical exploration, a reminder that our understanding of the universe is constantly evolving, and what seems like an impassable barrier today might be viewed differently tomorrow, even if fundamental laws hold true. Here's an old piece of folklore you might have heard, perhaps suggesting a clever trick to see the cosmos even when the sun is shining. The idea that if you look up from the bottom of a deep well, you can see stars during the day. It's a persistent image, perhaps conjuring up thoughts of a darkened shaft blocking out the bright sky. But this charming tale, while imaginative, falls squarely into the category of a space myth. Let's be clear, under normal circumstances, you cannot see stars from the bottom of a well during the daytime. The reason goes back to something we discussed earlier, the scattering of sunlight in Earth's atmosphere. Even if you are at the bottom of a well, the shaft only narrows your field of view of the sky. It doesn't significantly reduce the overall amount of bright, scattered sunlight that fills the atmosphere and reaches your eyes. Think of the daytime sky as being illuminated by a very bright diffuse light source, the scattered sunlight. This bright background light overwhelms the much fainter light coming from distant stars. Stars, even the closest ones, are incredibly far away, and their light is much less intense than the sunlight scattered by our atmosphere during the day. While it's true that, in extremely dark and clear conditions, someone with exceptional eyesight might be able to glimpse one or possibly two of the very brightest stars or planets like Venus, which is sometimes visible during the day if you know exactly where to look from the ground, doing so from the bottom of a well doesn't fundamentally change the physics of light and atmospheric scattering. The narrow opening of the well might slightly reduce glare from the immediate horizon, but the column of air above you within that opening is still filled with scattering sunlight. The light from the distant stars simply isn't intense enough to compete with the brightness of the daytime sky, whether you're standing in an open field or looking up from a narrow shaft. In essence, the well provides a limited view, but it doesn't create the necessary conditions of darkness required to make the faint starlight visible against the bright atmospheric background. The night sky is dark because that scattered sunlight source is gone, allowing the light from distant stars to dominate. So, while the story of seeing stars from a well is a nice piece of folklore, it's important to understand that the brightness of our daytime atmosphere is the real reason why stars are hidden during the day, a condition that a well simply doesn't negate effectively. We've navigated through space from the sun to distant galaxies, debunking myths along the way. Now, let's turn our attention back to our closest celestial neighbor, the Moon, and address a very common misconception about why it appears to change shape in the night sky. You've probably heard or even thought yourself that the different phases of the Moon, from a sliver of a crescent to a full, bright disk, are caused by the Earth casting a shadow on the Moon. This is a classic myth, and while the Earth's shadow does play a role in a specific celestial event, it's not what causes the regular monthly phases. The truth behind the Moon's phases lies in geometry and perspective, specifically the changing angles at which we view the sunlit portion of the Moon as it orbits our planet. Think of the Moon as a ball in space, constantly being illuminated by the sun from one side. Just like Earth, half of the Moon is always lit by the sun at any given time, and the other half is in darkness. What we see from Earth depends entirely on how much of that sunlit half is facing us as the Moon travels in its elliptical orbit around us. Let's walk through the cycle. The phase we call the new moon occurs when the Moon is positioned roughly between the Earth and the Sun. From our perspective, we are looking at the Moon's night side, the half that is not illuminated by the sun. Because the sunlit side is facing away from us, the Moon appears dark or is invisible in the night sky. As the Moon continues its orbit, it moves out from between the Earth and the Sun. A tiny sliver of the sunlit side becomes visible to us, which we see as a crescent moon. This crescent grows larger each night as more of the illuminated hemisphere becomes visible. About a week after the new moon, the Moon has moved about a quarter of the way through its orbit. At this point, the Sun, Earth, and Moon are roughly at a 90-degree angle. We see exactly half of the sunlit side and half of the dark side, which we call the first quarter moon. The illuminated portion we see continues to grow, resulting in a gibbous phase where more than half the Moon is lit but it's not yet full. The full moon occurs when the Moon is on the opposite side of the Earth from the Sun. In this alignment, the entire sunlit half of the Moon is facing us, making the Moon appear as a complete bright disk in the night sky. After the full moon, the cycle reverses. The illuminated portion we see begins to shrink as the Moon continues its orbit. It goes through the gibbous phase again, then the last quarter moon again, half illuminated, but this time the opposite half from the first quarter, followed by a shrinking crescent, until it returns to the new moon phase, completing its roughly 29.5-day cycle. So, the changing appearance of the Moon isn't about something blocking the light. It's about the angle at which we're viewing the Moon's eternally sunlit half. The Earth's shadow only comes into play during a lunar eclipse, a much rarer event that happens when the Earth passes directly between the Sun and a full moon, casting its shadow onto the Moon. But the regular, predictable phases we see every month are a beautiful demonstration of celestial mechanics and our shifting perspective on our illuminated satellite. It's a celestial dance of light and shadow, determined by the relative positions of the Sun, Earth, and Moon, not by our planet's shadow routinely covering our lunar companion. So, we've journeyed through space, challenging some pretty stubborn ideas about our universe. We saw that the Sun isn't yellow, the Great Wall isn't visible from space with the naked eye, and the Moon landing was definitely real, not a Hollywood set. We found out that asteroid belts aren't cosmic minefields, that gravity exists everywhere, even in space where astronauts float, and that black holes aren't just indiscriminate vacuum cleaners. We also learned that space isn't a perfect vacuum. The Sun's powered by fusion, not fire, and liquid water exists on worlds far colder than Earth, hidden beneath icy crusts. Remember those Martian canals, just optical illusions, not alien engineering. And the next time you see a supernova in a movie with a loud boom, you'll know that sound needs a medium and space is mostly silent. We also straightened out that planets aren't neatly lined up. Fire needs oxygen and doesn't rage in the vacuum, and the scale of the solar system is much grander than diagrams often show. Plus, you wouldn't instantly freeze or explode without a spacesuit, and the dark side of the Moon isn't always dark. Both sides get sunshine. We saw that seeing stars is looking into the past, that space isn't totally silent but has its own forms of energy we can detect, and Saturn's rings are made of countless icy particles, not solid disks. We clarified that the Moon isn't bigger than the Sun during an eclipse. The universe isn't just the part we can see, and space isn't simply black nothingness between stars. And those beautiful nebulae aren't small clouds but colossal stellar nurseries. We also confirmed planets and moons aren't perfectly smooth. Earth's gravity isn't uniform. Black holes might emit radiation, and planetary atmospheres are constantly in motion. We talked about how the Big Bang wasn't an explosion in space but the expansion of space, that Pluto's reclassification wasn't arbitrary but based on scientific definition, and that the asteroid that killed the dinosaurs wasn't necessarily the biggest impactor ever, but one in a particularly vulnerable location. Finally, we recognized how space exploration benefits us daily, and that while we can't break the speed of light, theoretically manipulating space-time might open future possibilities. And that old tale about seeing stars from a well, just a story, and the Moon's phases are about how much of the sunlit side we see, not the Earth's shadow. We also learned that while the North Star is important, it's not the brightest, that gravity's laws are universal even though its strength varies, and that humanity is an integral part of the universe made of star stuff. It's clear that our scientific understanding of the cosmos constantly challenges and refines what we thought we knew. This journey through debunked myths isn't about proving anyone wrong, but about celebrating the incredible progress of science and the ever-growing picture it paints of the universe. It shows us the importance of curiosity, of asking questions, and of relying on evidence and rigorous investigation to uncover the truth. The universe is a place of astonishing complexity and beauty, far stranger and more wonderful than many of the myths we've discussed. Every debunked myth opens the door to a truer, more fascinating reality, revealing just how much more there is to explore and understand. The mysteries that remain are far more compelling than the ones we've solved. So, what was the biggest space myth you believed before watching this video? Share your thoughts in the comments below. I'd love to hear which of these surprised you the most. If you enjoyed this cosmic myth-busting adventure, please give this video a like. It really helps the channel. And if you want to keep exploring the wonders and mysteries of space with us, make sure to subscribe and hit that notification bell so you don't miss our future videos. Thank you so much for watching and joining me on this journey through the cosmos. Until next time, keep looking up and keep questioning